Good morning to everyone present here and the audience who have joined us online. Myself, Hitaishi P from Electronics Department, will be the MC for today's program. Guru Brahma, Guru Vishnu, Guru Devo Maheshwaraha, Guru Sakshat Parabrahma, Tasmai Shri Gurave Namaha. Education is our passport to the future for tomorrow and belongs to the people who prepare for it today. A teacher who is selfless, devoted, hardworking, and the wisest person in the class. So I wish you all a happy Teachers' Day for one and all present here. It gives me an immense pleasure to welcome you all for 2 weeks faculty development program on VLSI design, technology, and architecture for biomedical application, that is from 5th September to 15th September 2022, organized by BIT in association with Electronics and Communication Engineering Research Center, BIT Bangalore. At the outset, I sincerely thank our management, Rajya Ukkalitra Sangha, and its office bearers for their encouragement and their support for the program. The technical co-sponsored by IEEE Circuit and the System Society Bangalore chapter. Now we will have our traditional auspicious lamp lighting ceremony as a tribute to Mother Saraswati. I welcome all the dignitaries on the dais. Ganesh. It is a mark of our underlying tradition to invoke the Almighty at the beginning of an important event. It is said one song can change a moment, one idea can change the world, one step can change the journey, but a prayer can change the impossible to possible. Let us raise for the prayer by Professor Swati, Assistant Professor from Department of ECE, BIT.
ಶರಣು ಸಿದ್ಧಿ ವಿನಾಯಕ ಶರಣು ವಿದ್ಯ ಪ್ರದಾಯಕ ಶರಣು ಸಿದ್ಧಿ ವಿನಾಯಕ ಶರಣು ವಿದ್ಯ ಪ್ರದಾಯಕ ಶರಣು ಪಾರ್ವತಿ ತನಯ ಮೂರ್ತಿ ಶರಣು ಮೂಷಿಕ ವಾಹನ ಶರಣು ಸಿದ್ಧಿ ವಿನಾಯಕ. ನಿಟಿಲ ನೇತ್ರನೆ ದೇವಿ ಸುತನೆ ನಾಗಭೂಷಣ ಪ್ರಿಯನೇ ನಿಟಿಲ ನೇತ್ರನೆ ದೇವಿ ಸುತನೆ ನಾಗಭೂಷಣ ಪ್ರಿಯನೇ ತಟಿಲ ತಾಂಕಿಟ ಕೋಮಲಾಂಗನೆ ಕರ್ಣಕುಂಡಲಧಾರನೆ ತಕಿಲ ತಾಂಕಿತ ಕೋಮಲಾಂಗನೆ ಕರ್ಣಕುಂಡಲಧಾರನೆ ಶರಣು ಸಿದ್ಧಿ ವಿನಾಯಕ ಶರಣು ಸಿದ್ಧಿ ವಿನಾಯಕ. Thank you.
Now the welcome address by Dr. Hemant Kumar, HOD of ECE Department. Now we'll have a traditional auspicious lamp lighting ceremony as a tribute to Mother Saraswati, the goddess of knowledge.
Asatoma Sadgamaya Tamasoma Jyotirgamaya Mrityoma Amritam Om Shanti Shanti Shanti.
Saka.
Now welcome address by Dr. Hemant Kumar, Head of the Department Electronics and Communication Engineering, Bangalore Institute of Technology. Over to you, sir.
Thank you. On Teachers' Day, I am full of gratitude for the invaluable contributions in nurturing power of human mind and inculcating indomitable spirits in students. Tribute to great educationalist and ex-president Dr. S. Radhakrishnan. We the teachers are the backbone of nation. They are the cause of change and revolution in and around the world. BIT, in association with ECE and IEEE, presents to you a 2-week FTP program on VLSI design, technology, and architecture for biomedical applications. IEEE is the trusted voice for engineering, computing, technology, information around the globe. IEEE is the world's largest technical professional organization dedicated to advancing technology for the benefit of humanity. For over a century, IEEE has sponsored various programs to honor achievements in education, industry, research, and services, celebrating distinguished colleagues, teachers, and corporate leaders who have made a lasting impact on humanity, technology, and professionalism. Learn about the organization includes its structure, leadership, and employees. IEEE CAS, which is Circuit and System Society, is the leading organization that promotes the advancement of theory, analysis, design, tool, and implementation of circuits and systems. The field spans the theoretical foundation, application, and architecture, as well as circuit and system implementation of algorithm for signals and information processing. The society brings engineering, research, scientists, and other involved in circuit and system application access to the industry, most essential technical information, networking opportunities, career development tools, and many other exclusive benefits. It's my pleasure to walk you through the FTP, introduce you to the speakers and delegates that have come from all over the country today to share their knowledge and enhance our mental horizon. Today's FDP has about 40 participants participating from more than 30 institutes from all over the country and across India, making this FDP a truly skilled FDP in spirit. Such FDP was the only way people could enhance their knowledge and share a difference of opinion on a common platform. We have surpassed the various challenges that our education system has faced over the years and has adapted to the changing technological trends in the industry. Last but not least, I would like to thank all the delegates, the staff, researchers, principal, management for giving us an opportunity to conduct this 2-day long FDP program at BIT ECE. I would like to welcome first and foremost LM Patnaik, advisor, BIT, to this 2-day FDP program. Welcome, sir. Thank you, sir, for accepting our invitation to grace this occasion. And I would like to welcome our backbone of our institute, Dr. M.U. Ashwath, Principal, BIT, for his constant encouragement and support to conduct this FDP program. I welcome you, sir. And I would like to welcome the other dignitary, Vice Principal, Dr. Jay Prakash, for this inaugural ceremony. Welcome you, sir. And I would like to welcome our Academic Dean, Dr. H.P. Balakrishna, Professor and Head Department of Civil Engineering, for this occasion. Thank you, sir. And last but not least, I would like to thank my fellow colleagues, who is PG coordinator for the VLSI design and in charge coordinator for the new VLSI program, which has been instituted in UG level at the institute for the first time in the country and in the state. I would like to welcome Dr. Vijay Prakash for this inaugural ceremony. Welcome you, sir. And one more colleague, Dr. C.R. Bhaira Reddy, I would like to welcome to this gathering. I would like to welcome, sir. But not at last, not but at least I would like to welcome all my HODs who have been constantly encouraged to be a part of this FDP inaugural ceremony. Thank you. And I would like to thank the staff and students of this program who are participants and their skills are to be enhanced through this FDP. I would like to welcome you all. I would like to conclude my speech by encouraging the delegates to participate with an increasing number in all the activities and discussion through the digital platform for the next 10 days. I wish everyone a successful, safe, and fruitful FDP program. Thank you.
Thank you, sir. Now, the faculty development program highlights will be given by Dr. Vijay Prakash, sir. Over to you, sir.
Good morning, one and all. Happy Teachers Day. Respected principals, Dr. Ashwath sir, Dr. LMP sir, Vice Principal Sir Dr. Prakash, our beloved HOD Dr. Hemant Kumar, all the deans of the VITs, HODs from the different department, placement officer, all teaching and non-teaching colleagues of EC department, faculty from other department, organizers of the FDP, and all the participants across the nation who are joined remotely, and respectful speakers of the faculty development program. I'm Dr. Vijay Prakash, Professor, Department of ECE. It's my privilege to share the overview of 2 weeks of faculty development program on VLSI design technology and architecture for medical applications. The purpose of this FDP is to encourage and reward existing faculty for developing their teaching and practical skills in VLSI design and VLSI for medical applications. The FDP contains 2 themes. The first one is the VLSI technology and how effectively the VLSI architecture can be used for medical applications. Dear participants, in this present era, healthcare becoming expensive with rising cost and an aging population, where on the other hand, the government is unable to allocate expense for them. Due to these problems, patients are undergoing trauma and feeling difficulty to avail medical services and expenses. In this case, wireless communication reduces the cost and patient suffering. This wireless system can be implemented using very large scale integration. So which is applicable for biomedical applications. Using VLSI methods and VLSI architecture in neurology helps to reduce the size of the circuits and systems, area and improvement over the speed requirements. VLSI will improve the cost effectiveness of medical devices through advanced low power, smaller size, high speed circuitry and systems, which provides increased sophisticated enhanced functionality. So VLSI technology has opened up vast avenue for career growth in design, analysis, design implementation, computer-aided design, verification, simulation, and testing. Very large scale integration is a solid career choice and offers job opportunities for ECE freshers pursuing core employment in India and overseas. So VLSI provides variety of employment roles featuring outstanding professional growth and salary incentives. So one good news is the Indian government planning to invest nearly 1 crore lakhs to enhance the semiconductor industry and planning to start fabrication unit in Mysore. But considering all the above facts, BIT ECE conducting 2 weeks FTP program. So VLSI professionals are always in high demand for ever evolving industry. They have a very bright future in VLSI industry. The digital world is made up of a variety of electronic equipments such as automation, devices, gadgets, and so on. All of which are controlled by a chip or integrated circuit. Some of the following areas are major domains of the VLSI industry with great potential for the growth: analog layout design, RTL design, design verification, design for testing, physical design, and so on. Dear delegates, so in these 2 weeks FTP, some of the major topics what we are going to cover. So the day one start with the recent trends in VLSI design will cover 2.5D and 3D stacking systems, followed by the cost, size, and security in chip design. So day two, so we're going to start with AI for medical imaging and practical implementation of AI algorithms for medical imaging and early breast cancer detection algorithms and how to implement this using VLSI architecture perspective point of view. So day three is medical imaging analysis using Python and how effectively we can implement by Microsoft VLSI architecture. Day four start with application of microelectronics and how to implement biomedical engineering using VLSI approach. Day 5 and day 6 will be covering neuromorphic computing and VLSI implementation of neuromorphic algorithms. So how neuromorphic algorithms are mimic the brain systems and how to implement by Microsoft VLSI approach that we are going to cover in day 7. Day 8 hands-on session implement how to implement the VLSI algorithms by Microsoft simulation tool like Model Sim. Day 9 we are going to cover the basic physical VLSI physical design by Microsoft Cadence EDA tool. The last day of the program, smart sensors and the systems for biomedical applications. Dear colleagues, dear delegates, so in each of the session, the application of advanced VLSI circuits and medical imaging is explored. The relationship of both general purpose signal processing and signal processing chips and the custom devices to medical imaging is discussed using examples of fabricated chips. Dear delegates, in these two weeks of FDP is very much essential for present day scenario. I hope all of you make use of this technical event and enjoy the 2 weeks program. After attending this mega event, the participants will get in-depth understanding of research and its implications in decision-making process in VLSI design and medical imaging. So with this, once again, welcome you all for this mega technical event, 2-week FDP program on VLSI technology and medical applications. Thank you, Ananda.
Thank you, sir. Now I request inaugural address by Dr. L.M. Patnaik, sir.
Principal Dr. Ashwat, Vice Principal Dr. Prakash, HOD Dr. Hemant Kumar, and Dr. Civilian and Dr. Balkistan, Dean Sir, Dr. Vijay Prakash, Bharati, and one of the main coordinators, Professor Janada, HODs, and faculty members of the department. I hope you are able to hear. Because every time I speak in BIT, they say there is a mic problem. Okay. At the outset, let me convey to you all my warmest greetings on the occasion of the Teachers' Day. It is very nice and befitting that BIT is organizing this event on this auspicious day to enrich the background of teachers along with teachers. There is no other better tribute you could have done to good teaching and teachers, to encourage teaching. I would like to congratulate the organizers and the institute for organizing this particular event. The topic is really extremely relevant, and IEEE is involved in that. If you look at IEEE's logo, below IEEE 4 letters, it is written Technology for Humanity. It is written in smaller letters. You find that. So what IEEE conveys, your technology, what you develop, should be for the humanity. So there is no better application you could think of other than healthcare. In fact, COVID has opened our eyes. It has put a lot of challenges. There are two areas where we had really very stiff challenge and we were caught unawares. We didn't know what to do. One is education, second is healthcare. Okay. Up to COVID time, pre-COVID, we were doing online education, distance education, whatever it may be. And in healthcare, there was a concept of telemedicine and all that. But then COVID put the biggest challenge for these two areas. That is education and healthcare. And we were all driven homewards. We were confined to the four walls of our home. We were, the world outside was spinning. There were excellent meetings, conferences. Young students were dating, people were drinking, there were seminars, there were lectures, but all sitting inside the rooms and everything was happening behind the screen. Okay? So it is all thanks to technology. And I think this mode is going to continue for quite some time in future in some form or the other. So this particular FDP is talking about an interesting area, that is VLSI design technology and architecture for biomedical applications. It's a very good combination. The day I started interacting with BIT, I said one of the good application study in this campus is medical application, because we have our neighbors and a set of experts who are doctors. We should be talking to them and think of a lot of applications of civil engineering, mechanical engineering, electrical, electronics, computer science for medical profession. Now, you know, across the country, every IIT, even including a sort of traditional institution like IISc, they are all going to have medical schools in their campus. Okay? IISc is going to have a hospital, the research facility. IIT Madras, Delhi, Guwahati, all of them are going to start some medical schools and centers. They don't have anything, they're going to start from scratch. But we have something next door to us, they are our neighbors. We should be talking to them rather than closing our eyes and ears. We can do a lot of things. VLSI, as was mentioned by my predecessor, distinguished speakers, is a very important area, as was mentioned. It's very large scale integration. Today, you see the power of a computer on this, which were done on a supercomputer probably a decade ago, or 2 decades, or 3 decades ago. Now you find that as this. The chips are extremely powerful. You don't know what you will do with it. All these advances in 5G, 6G, and beyond that 7G, if at all it comes, are thanks to VLSI technology. Because what happens here, you are packing more and more billions and billions of transistors on a single chip, which is probably few centimeters by few centimeters. Okay. So that is what is called integration. We started with a small scale integration, medium scale integration, large scale integration, very large scale integration. Then you talk about ultra large scale integration. Now the resolutions are going further down and down. You talk about submicron technology, deep submicron technology. And if you look at the problems of deep submicron technology, sometimes you use the concepts of electromagnetic waves, how a wave transmits over an RC network. There are a lot of interesting problems there. Our Dean sir was talking about the initiative in Mysore, chip fabrication. This country is very late. We don't have a fab facility. PL manufactures some chips. Probably they are not of really great consequence. We had a semiconductor complex in Chandigarh, which got in a fire accident. Later on, space and defense took over. Defense has some interest. So we never realized the importance of this, never set up a fab facility. Now, you can't expect any multinational company to be coming and investing because it is a billion-dollar investment. They will say, why should we do it? And things phase out very fast. Okay? It is good that the country has realized now we have a fab facility. Since we don't have a fab facility for space, defense, atomic energy, everything, we have to go to either Taiwan, Singapore, or Korea, some country in their foundry, we have to get the chip manufactured. For a defense application, it is highly insecure because they can put some chips without your knowledge and detect the signal. They can do some amount of sort of secretive investigation and monitoring that thing, putting some high frequency design chips and circuits there, which you will not know. They will have additional pins and get the signals and try to do something. That is why now there is a new area which is coming up, design for trust. How do you believe the chip, what is manufactured somewhere? So there is another useful thing for which I would like to congratulate BIT. You have started this program on VLSI, okay, which is timely. In fact, suddenly everybody is realizing VLSI is not only very large scale integration, it is very large source of income. VLSI, okay. You will find there are a lot of jobs there, okay. A lot of business, chip making, fabrication, all that stuff. There will be demand of electronics engineers, computer engineers who will be required to run this business, okay. Maybe even physicists, okay. Mechanical engineers, okay. Then high temperature systems, how to maintain. There are a lot of things which will come up in this particular stream. In fact, if you look at the CAD, what the Dean sir was mentioning, CAD is not an electronics activity. It is totally computer science. There are algorithms, maths, theory, coding and all that. What you see, Cadence design tool, which is nothing but maybe millions of lines of code, which is all maths, code, data structures, algorithms, everything. Because by any chip design, put very briefly, you start with a high-level specification, what the chip has to do, what the microprocessor has to do, what the ASIC has to do, and from that, we get into what next step called something like a synthesis, okay? You want to synthesize using some AND gates, NAND gates, NOR gates, and things like that, how do you do? From that, How do you implement that using transistors? You will get next step, how many transistors and where these will be placed. So this is what is called placement. And if the transistor is placed, transistor has been, this has some input, output, how to route them, connect them. So there is a placement, there is a routing. These are all computer science algorithms. Like there is a rectangular box, how can you fit? There is a chip, how can you fit so many smaller elements into that? It is an algorithm problem for computer science. And next comes routing. How do you interconnect? There are things like maze routing, number of things. Because when you route this printed circuit boards or VLSI, there is a problem. You cannot route inclined lines. They have to be horizontal or vertical. You cannot do any way you like. You can't do crisscrossing. There are some constraints. So there are packages for that. Next, after doing that, we look at something called its behavior. Much prior to that, synthesis, whether they meet the time requirement somewhere, it has to have some requirement of timing. Does it meet that thing? After that next step at the final end, you will get into what is called a testing. Okay. You design a chip. Does it meet the requirement? Does it work? You have test vectors. Does it give the right type of output at the end? Okay. In fact, the yield will not be 100%. You will reject most of the chips. You will throw them out. Okay. So what test vectors you will develop? So it has a number of these steps: placement, routing, synthesis. Then because you cannot actually build the chip with millions of them, we do simulation. Simulation is a time computing process. You do logic simulation, whether it gives logic 1, 0 correctly at right points. You do what is called circuit simulation, the exact values of voltages and current. So all these things are good interplay between electronics engineers and computer science people. And when you talk about a tool like Cadence, I'm happy to know that BIT has that. Most institutions don't have Cadence. Cadence is a very expensive thing. Okay? It's good for a timing analysis. You can do wonderful things using that chip. And using this, you can do a lot of interesting research. And what we are looking at is biomedical applications. VLSI chip for what? Is it 5G, 6G? Maybe you can think of IoT. Here you are talking about biomedical applications involving signal processing and all that stuff, where you can use, add, multiply this type of chips and implement that. So that anything you do by hardware is going to be faster when it is done in software. That's why people are now these days excited about doing it by hardware. So this combination is good. Not many people look at that. Healthcare, biomedical applications. Only you will have to think about what type of applications you have. Maybe one can have patents, industry, startups, number of things. So I would like to congratulate the organizers who are organizing this, and thank you very much for giving me an opportunity to you. There are a lot of exciting things in fabrications and store. They are talking about 3D manufacturing, 3D chips and all. How do you have so that you can pack more and more intense things? And I noticed there is a keynote talk from someone industry. Okay, they will talk about a lot more things because in terms of fabrication technology, ASICs, what we call SOCs, okay, application specific integrated circuits, the trends. You need to know a lot more what is happening. And sometimes we can't fabricate the chip. It's a very expensive process. Nobody fabricates 1 or 2 chips. You have to pay maybe several thousands of rupees, even if you want to send some of the designs outside Korea or Taiwan. No one will manufacture 1 or 2. But there are some educational academic packages, tools where you can participate. Even tools also, there is a public domain tools like Magic and other things. You can get some hands-on. But luckily you have Cadence here, and you can develop some chips design, and these can be tested using what you call FPGA. I'm told you have an FPGA lab, so using FPGAs, you can test those things, whether it meets the timing requirement and all that things. That is what we call something like poor man's VLSI. If you don't have any chip, you can at least test these things. So everything you conceive of, any electronic equipment product, biomedical, your mobile, the best of the 5G, 6G, chips communication. It is thanks to VLSI. If VLSI were not there, you could not have got this type of functionality, this type of miniaturing. It is impossible. What was in your desktop, as I said several years ago, now you are holding in your palm. And you don't know what will happen, even when you are talking about a computer being on your wrist and all. It's all thanks to VLSI. Okay? I hope you will have a wonderful time during these 10 days, have great fun, and take this knowledge and do impart a good post program curriculum to your students. More important thing is about. Thank you. It's my pleasure to formally inaugurate.
Thank you, sir, for your information regarding VLSI technology. Now I request Dr. H.P. Balakrishna, Head of the Department Civil Engineering, BIT, to address the gathering with few words.
Thank you. Good morning, everybody. Happy Teachers' Day. My role as Dean Academics is to educate faculty members of our institute to deliver knowledge to the students as well as share with faculty members. This faculty development program is very apt for the occasion because health industry is facing a lot of issues in detection and curing diseases. This faculty development program will throw light on detecting the disease and helping the doctors to reduce the time of identifying the disease and the way to cure. So I wish the faculty members, the participants, very best and learn to the maximum extent and implement all of those things in future. I thank Dr. Hemant Kumar, Head of the Department Electronics and Communication Engineering, Dr. Jalja Madam, Professor Vijay Prakash Baira Reddy for giving us an opportunity to share our few thoughts. And I wish you all the best once again. I wish all the participants all the best. Thank you.
Thank you, sir. Now I request Dr. Jai Prakash, sir, Vice Principal, BIT, to address the gathering.
Very good morning to all of you. Dignitaries on the dais and off the dais. Today, the Department of Electronics and Communication Engineering, so they have initiated a very good program. Now that's a faculty development program on the VLSI combined with the biomedical field. Generally, if you think in professional education system, even today, two fields, one is the medicine and the other one is engineering, are the two main professional courses. Of course, many courses are available, but people even today select these two fields only mainly. Now, if you integrate these two fields, engineering and medicine, today's topic is definitely fit with in that context. So at this juncture, I want to remember in early 90s, Open and Safar has written, an algorithm for the two-dimensional fast Fourier transform computation. Even today, people are using that only. But it is for few signals only. If you use that particular algorithm to reconstruct image in MRI imaging system, even today, the same algorithm is used and the same method is used for reconstructing images, even for the slicing, millimeter slicing, the algorithm is same. But the algorithm has been in the form of hardware using the VLSI technology, and the reconstruction of the images has been done on real time, which definitely indicates the relation of engineering and the medicine in terms of this biomedical, especially in the oncology field, for the analysis, diagnosis and analysis, and even to give a medicine also, target medicines. Definitely engineering plays a very important role. Now in the FDP, so if I had seen that topics, including biomedical applications, then VLSI architecture and applications. Even today, the inaugural address is going to be given by one of the very good company, that's the Intel people, I think, Biswajit. If you recall, where Intel started in 1960s, 1962, they have started with 4-bit processor, and today they are in i7 or i10 processor with 64-bit processor. Just to imagine what is the role of VLSI from 4-bit to 64-bit process. Therefore, definitely this very large scale integration technology plays a very important role, not only in engineering, not only in semiconductor field, but it also equally plays a very important role in healthcare systems also. Hence, the content of this particular FDP is suitable to the present context. I really thankful to the organizers. They have taken this particular concept and they have arranged an FDP to educate all the faculty members to deliver good things to their colleagues. I wish good luck to the organizers, and also I wish good luck to all the delegates. More than 50 people are attending around the country. They will get the hope, they will get the good information from the very good lecture delivered by the industry and the academicians, and they can meantime exchange their ideas with these academicians and industries. Wish you good luck to all to arrange this kind of FDP. Thank you very much.
Thank you so much, sir, for your kind words. Now the presidential address by Dr. M.U. Ashwath, sir, Principal, Bangalore Institute of Technology. Over to you, sir.
Good morning, and I wish on the occasion of Teachers' Day, all the participants, both offline and online attending. And I will not take much time, already it is delayed. I think the keynote speaker must be waiting to address all of you. In fact, we did 2 major programs, one just before COVID on technology for health, and one after the COVID-19. The same international conference on technology for health. So now, as Professor Patnaik also mentioned, the technology-oriented organizations like IISc and IITs are also starting medical related programs. And BIT is not lagging behind. BIT is also organizing similar programs at our campus. In fact, the first offline program on technology for health was conducted here in our campus, and more than 500 participants from across engineering and medical organizations participated in that. After that, as a progressive work from BIT, we signed MOUs with 2 major companies. One is Aventin Inc. USA and V Healthcare. These are the 2 organizations where we have MOUs to collaboratively work, merging technology for medical applications. And today's program is also mainly using VLSI technology and embedded systems and architecture for biomedical applications. We have 2 more programs, 2 more MOUs with Mistral Solutions and Capgemini, again working on VLSI and embedded systems. So I think the ecosystem at BIT is all set to take it forward, and I'm sure this 10-day faculty development program will also give some ability to work in these areas and using applications of technology for medical use. And I wish the organizers all the best, and all the participants
I hope you will have a good value added knowledge dissemination in the next 10 days. And thank you once again. And I welcome all the participants outside BIT to come to BIT and use all the facilities available at our institute. Thank you very much.
Thank you, sir. Now the keynote address will be given by Professor Gahan, Assistant Professor, Bangalore Institute of Technology. Our keynote speaker is Dr. Biswajit Pat from Intel India. He is a Senior Director Technology, and by nomination he is a Senior Principal Engineer. And the introduction of Dr. Biswajit Patta sir will be given by Gahan AV, Assistant Professor, BIT.
Good morning, one and all present here. The keynote speaker for today's session is Dr. Biswajit Patra. Biswajit Patra has been working in Intel India as a Senior Director Technology, Senior Principal Engineer by nomination to design low power and high performance and high volume SoC in advanced technology nodes for AI/ML, heterogeneous and mobile computing. Previously worked as a Principal Engineer in SoC Physical Design at Qualcomm, Bangalore, India. He has completed his PhD in Computer Science and MTech in ECE from Calcutta University, effective leadership and management from the Eli Broad College of Business, Michigan State University. Biswajit has demonstrated his technical leadership in product mission critical functionalities like 3D IC, SoC power supply design, SoC lifetime reliability, PCB package SoC co-optimization, low power, high performance SoC design, and thermal modeling in multiple time create strategic and business critical products, deploying high performance XPUs and advanced technologies for nodes for mobile, laptop, xScale computing, and AI supercomputer. He's been author for more than 40 papers in national and international journals and conference in low power SoC design. He's very passionate about mentoring, fostering, influencing career growth for technical leaders across the globe, enhancing the technical capability of the team, achieve excellence as Innovation Forum Technical Chair, has been driving the team with more than 2,000 plus highly motivated engineers towards generating new idea, increasing strategic patents, improving product readiness and quality of execution. Biswajit has been working as a mentor in Intel India's flagship startup program, engage these deep technology startups. I welcome you, sir, for the 2 weeks faculty development program. Thank you.
Thank you so much. Very, very good morning to all. And I think what a day today is a Teachers' Day, and then we are talking in front of the teachers. With all of you, we have learned a lot, and we all have a highest regard to the teachers. So on behalf of Intel and on behalf of myself, thank you for inviting me in this great occasion, particularly on the Teachers' Day. And thank you all professors, the teaching community, on this special day. Wish you all a great day, and let's get started. So, are you able to see my desktop? I'm just sharing the content. Is it visible, Dr. Jalaja?
Yes.
Okay, very good. So, thanks for the nice introductions. And the topics of the discussion is basically today, the biomedical automation is one of the key items. And we have seen during the COVID time that how the technology has transformed ourselves, be in the working from home. Many of us has worked seamlessly, probably for a 2 years kind of a time duration from home, or some kind of an off and on. In many cases, doctors were consulting the patient through online platform, giving the medicines and keeping a track of the patients. So this is a great time in terms of the technology explorations, what has happened recently, to think in that way. And with that, what I'll be starting is saying that how can we really change the way we are thinking it today to thinking it tomorrow, and making the biomedical industries and the biomedical solutions for more user friendly, and people can use the technology for their daily uses. So that's the theme of the discussions, and we'll talk about how the VLSI technology in combinations with the IoT, the 5G, and the edge computing, along with the AI and ML, we can achieve that target. That's the kind of a framework I thought to put together. And the idea of this presentation is to ignite the thinking process in the academic community, show that the good amount of research work what you are doing it today, you can do some of this research in this area which will be benefiting the whole community and the students definitely. So that the thinking process, keeping in this mind, I thought to just put this in front of us, and let's brainstorm and ignite the fire within ourselves. That's the intent. So what we'll talk about today, you will see that the opportunity of biomedical technology explorations, and the VLSI, 3D IC, AI/ML, 5G, the technology, how can we create an 100x improvement of the current state of affairs over next 3 to 4 years horizon? And then the conclusions, that the whole framework we'll be talking about. And feel free to ask me a questions anytime. So I'll be love to do that, and we can do it after these sessions also. Now let's look at the today engineering has actually transformed from the pure engineering, the electronics devices and all, which more by and large used to be used for computing or used to be using some industrial automation. And the biomedicals is a great field where we can get the benefit of the technology for our own personal daily life. And let's think about where we wanted to go, where this industry wants to go over next 3 to 4 years. Ideally, each of us would like to see that we have a doctor 24/7 at my doorstep who will be giving me the guidance, giving me the help where it needed, and it suggests a lifestyle change which can help to give the doctor a prescription. Prescriptions is the second phase of it. At least at the first phase, it should produce the 99% accurate reporting, and then verified by a doctor that yes, this piece of biomedical instruments is actually giving the right information. So the doctors can still play a kind of a check and review role, but a machine like the cartoon what you see is can act as a doctor for you, and 24/7 available at your doorstep at your mobile app. That's what all of us love to see it, so that our body is being continuously monitored in a safest manner with the data privacy keeping into mind, so that my information doesn't go to anybody else. And if you look at it, the list of instruments today, it's available to find out any kind of problem in our human body. We try to do the CT scan, we do the mammogram, we do the MRI for the upper part, the lower part also, sometimes we use the MRI, we use the X-ray, we use the different portion of the segment to do it. And human body is very complex. If you see it today, human body, we are all living in the life of bacteria. That basically means we have almost 40 trillions kind of a cells, and we have a 10x more number of bacteria in our body. That's how we all live. We work with bacteria, but the bacteria mass is much more lower. It's almost like a 1 to 3 kgs of bacteria you are all consuming. And there are different school of research, because this exact finding out is not that easy. That's why you may see some literature talking about Israel recently has done a research and talking about probably it's not 1:10 that for every cell there is a 10x more bacteria. It's probably 1:1 they have come across. So let's leave aside that maybe they have done the sample testing in a smaller scale. Maybe sample testing was done on a healthy environment. In and out, we have 1:10 bacteria in our body. Now, the machine is very important one. If we can have a device which can detect and personalize the medicine for you, if it can be produce a medicine based on your body structure, taking the capabilities of AI and ML in a fastest possible manner, how much benefit you get it? You just take the drug, what is absolutely needed for you. So the benefit and then the imaginations where we go is humongous. And here, why I would like to put this file here in front of this academic community to ignite the research process so that we can reach there. The industry alone cannot do this all research work, where the research work need to be done in a combination of both the environment where we can go to the fastest possible manner. So that the kind of an essence of this file, what I would like to paint in front of you, and you guys know much more better than me in terms of the theory and each part of the where we will be connecting that, or probably industry can play a role of connecting the dot, and you can play the role of doing the research of individual area. Where a lot of startups, one startup recently, I know I was mentoring, I can't take the name of it, but they are struggling to see the same data scientist who is looking at the MRI for let's say the brain. It's very difficult for him to interpret the same MRI what you are taking it for, let's say, lower abdomen. It's a completely different study, and each company cannot really cover all the dot together. That's why you're probably seeing that a lot of startups are there which covering the each portions of the body design and trying to find out an algorithms which can detect and tell the disease looking at a particular stuff, because it needs engineering, it needs an AI ML, it needs the doctor interpretations. So you need to all of this to be coming together. Before this presentation, professor was talking about that in IISc or every IITs there will be a medical institute. That's the reason where engineering and medical merge together and create a environment which can help the mankind. Help the mankind doing the reverse engineering of our body so that we can actually don't need a medicines. That's the kind of a scheme where we need to think about in our next 1 decade or so. So that's the thought process I would like to build over to each of our mind so that we can do the research in each of the individual areas and contribute to the ocean. It cannot be done by a single person or a single organization or a single institute to solve the whole paradigm by a single company. It's not possible. So let's be very clear over that. Now, you must have noticed out this second phenomenon where basically we are from Intel and we would like to keep the Moore's law alive, which basically means in every 1.5 year time frame, we would like to increase the packing density of the transistors by 2x or even more. Now, the question is, maybe you have heard about 128 nanometer, then 60, 90, 25. Now it's going mostly 5 nanometer, 4 nanometer, 3 nanometer, all this term. Then what next? That is still is an open question, but good amount of research is happening. If you look at the MIT's, the technology review, which was published recently, they've done a significant good amount of progress in carbon nanotube, where a single carbon atom can be working as a transistor. So think about this. If this is when this technology will be commercialized and available, the size of the CPU or size of the SoC will be further reducing by an order of 100, 200x or even more. Maybe the capacity will be constant not by the transistor size, but because of the heat it produces. Now the carbon has its own another advantage. It produces a lesser amount of heat compared to what it is produced by the regular transistors. So it needs a wide amount of research work to be done to create an infrastructure, create a kind of a VLSI technology where the carbon single carbon atom can be used for synthesis to do the design for testing, to design for all the schemes what we are doing for the regular domain today. How do we really map that to a single carbon atom based structures in future? That's the huge amount of research happening in MIT, Stanford, and then quite a good amount of universities. How do we really leverage and capitalize in our academic community, do the research on this area and clear path the innovations for the future. If you have noticed out recently, the market is humongous, and the market what dictates the innovations. That's the one way of looking at it. If you see the human mankind of the whole world, even if we spend a 100 rupees per month, it creates a billions of dollars for this company to revenue generate the revenue. And if that take care of the health and it reduces your going to the hospital, it's a humongous benefit you will get over there. So the idea here is to how do you really create a technology which can help for the humankind? And that's the thinking process we need and the guidance and help from the academic community to do the research in this area. If you see, this is a very interesting article which is being published also in an year and a half back, where the Elon, you may have seen the chimpanzee along with Elon, it's a very famous one, where a chimpanzee's brain is modulated, and inside the brain there is a chip is being put inside, and through that chip we are able to instruct the chimpanzee what to do. Think about the innovations and the scale and the quantity and the health and how it can help these medical biomedical industries. Many of us, once we get aged or due to different reason of the other, our memory sometimes get lost. Sometimes a lot of people's, maybe in the whole world, there are millions of people whose memories are not working. Now, at this age-old problem, or there could be a problem at the even early age, how can you implant an SOC inside the brain, and that can act as an instruction giving by a machine, and you can give a better comfort of life to the person? What a humongous amount of beauty to the community to be done. So this is another very interesting research area to work on. And today, I think my focus will be mostly to see how our great academic community can create a research activity in India, and those activity can trigger the innovations in and around, and those dots, when we connect, we get a great innovations across, and India will be the number one in that game. That will be the kind of a scheme what I'm going to be talking about today on the Teacher's Day. Now let's look at an Intel, what we do and in terms of the VLSI technology. We continuously innovating to make sure that we have a cutting edge technology, be it the transistor, be the way we integrate the SoC so that it can produce a smallest possible size, the smallest possible power, and the highest possible performance. That's our goal, to produce and keeping and giving the industry a committed product which can create a customer's delight. This is one of the examples. If you see, we launched this product in 2019. We released in CES, in Las Vegas, where the idea was that if you look at this picture, this is a real picture, okay, an X-ray image of this. So you have a package. Inside the package, you have a two die. If you think about the two die, it in two different process. The below one, where you see the mouse, that is basically a 1222, or you can think about like a 22 nanometer, one die. On top of that, you see there is a 10 nanometer die sitting over there inside a package. And the beauty of this structure is you get a die, a overall footprint becomes smaller, because two die in a one on top of each other. Once you stack, like our building construction, you have a limited land, and how do you really go? You can go only up direction. So you put two die one top of each other to create that infrastructure. Now, when you create that, what's the benefit you get? The benefit you get is you get the smallest possible size, number one. Now, as we know, once your technology is going to be faster and faster, the leakage current, or in other words, when battery operated devices, when there's nothing is happening, a lot of current is getting leaked through the devices. So if you use this a lower technology node, low cost lower technology node, and only for the compute where you design the CPU, you take the high node and put on top of each other, you can get the best leakage benefit. So in these cases, we got a less than 2 milliamps kind of a leakage, which we productized this product. And this was all driven majorly from the Intel India. That's the great part. So innovation is happening in the India Geo. Definitely, it's an MNC company. We partner with every stakeholder on the worldwide. Nobody in the today's can do an independent work. That's practically impossible. Why I'm raising this point is requesting the academic community to collaborate within yourself and have a great research mind. Alone, you can't solve the world hunger. That's basically impossible. The complexity of the design is higher, and same principle today applied in the industry as well to solve a bigger problem. Now, when you do this kind of a design as an engineer, you have a lot of complexities. So the cartoon or the X-ray pictures, what I'm showing it over there, if you noticed out, when you stack the two die on top of each other, you see there is a problem in terms of the power delivery. The power need to come from the the, the backside bomb to the package through the TSV to the top die. So that through every power supply need to come through this. How do you make sure that every transistors here get the required power supply? Remember, a transistors work for a particular voltage, and each transistor, let's say in a device you have billions of transistors, you have to build a power delivery network which can support each transistor the required voltage. If one transistor doesn't get the required voltage, the device is dead. You can't use this. Right? So you have to design such a manner that power integrity is power delivery network is extremely designed flawlessly so that device work when you're getting out of the fab. You need to make sure that thermal, you think about this, when this die consume working on a CPU operation, it may be taking a lot of power, and then power need to dissipate by heat. When you have this kind of a complex structure, the heat need to dissipate and go out continuously so that the device doesn't get burned out. So you need to do a thermal analysis. When you create this kind of a technology innovations, you have to think about this device work, the stability and the reliability for a given period of time. And you need to do it very fast. If you don't do it, somebody else will do it. Remember that. And time to market is extremely critical, and the low power. Why I'm trying to put this thinking process to all of us, when you design something, you need to think about the multiple discipline into an accents. You need to design a systems. You need a power delivery persons. You need a thermal engineer to look at it. You need a reliability engineer to make sure that the transistor, the stacking, thermal, mechanical, that really works. And you need to make sure that all of this you do in an extremely laser focused, timely manner so that you can actually deliver the product. Ultimately, you are doing to deliver something tangible at the hand of the customer, and it has to be the low power. And all of these are very much applicable for the biomedical, and it's more relevant there because if tomorrow we would like to come up with a biomedical devices which goes inside our brain and act as a companion devices to enhance our memory capacity or enhance our memory power, it has to be extremely reliable. It should produce the minimum amount of heat possible. Our brain is about 12 watt is kind of a machine. You can think about that way. And each of the brain cell work with a 70 millivolt kind of a voltage. And today, if I really want to implant something, it has to match naturally with that 70 millivolt kind of a number to get out of something. So there is a complexity and the nitty-gritty of each of the item, and each of the item is a separate PhD topics to begin with. And we have to think about in that direction, how can we go in this vast area and create an expertise in the multiple disciplinary way, come together and solve this problem. Now, this product, when we launched, you think about this product. This product was, a complete motherboard was just like a, 25 cents. You keep one up there, you get the board size. So it has to be one. And think about this kind of a complex processors. Earlier, we used to build a big, desktop and one full table used to take. Today, the same equivalent functionality or even smarter functionality you are getting in your size of your palm, where just keep the 5, coins and you get that size. So what a kind of an improvement is being done. But should we feel good about it? Yes, we should. But should we stay there? No. We need to continuously innovate to make sure the survival of the humanity. That's the key questions. And at Intel, we are committed to it, and we all of us need to be committed to keep the progress going further. Maybe in after a couple of years, the whole things will be coming in a small, tiny, or instead of 5 coin, it will be becoming a 1 coin, which can do this whole operation. I'm not talking about the one SoC, it's the whole system you can design like this. Now, the next generation 3D stacking, where actually this was just simplistic structures what we tapped out in 2019, we commercially launched. And the next devices, which is your next generation's supercomputer, which will be used for a exascale computing. And this devices for that, we have released the Ponte Vecchio, which is in the oven. It already released by our the management Raja in last year. And if you look at it here, the reason I'm trying to show it about in this SoC, if you look at it, almost 47 in a chiplets or a small die we have embedded together to make a simple SoC. So when you try to do this 47 chiplets and you attach them, think about the mechanical complexity, think about the thermal complexity, think about the complexity associated with reliability. So all these angles you have to think together, visualize first before you do it. But once you imagine, you can do it. That's the kind of an innovations we need to think through. And when you try to make this kind of a product, you need to make sure that we do this. And why and how this help you today in biomedical instruments? It's extremely useful, because think about this, that today, if we would like to do a compute, a genome studies was not a new technology today. It was invented long back. 20 years back, kind of time frame, a lot of research, fundamental research has happened. But that time it was not so much popular because computation was not available. If you would like to do your genome test, genome sequence, and try to see what kind of disease, probably you will get it looking at the structure of the DNA or the probability of a particular disease to come, or particular kind of medicines is more useful for you and some medicines are not useful for you. If you get that piece of data at the beginning of your childhood, the entire lifestyle, you can modulate the kind of drugs you have to take it. And at couple of years back, the computational cost was too high that it was extremely difficult to do that. And today, if you see it with this kind of a platforms, what is getting built by Intel and then industry, it's just not the Intel, it's many companies are trying to build that. And we are committed to do that as well, where you can get this all analysis done in maybe in a week kind of time frame. Earlier, it used to take months and years in a computing platform, and cost of compute was a couple of $1 million, which was not being affordable by the general people. So there's a lot of research is needed where we can use this compute and use for the human benefit. Maybe a small, like a dongle kind of a stuff you attach tomorrow in your laptop, and you do a genome study at your home with a kit of maybe 10,000 rupees. And how do we really create that kind of a structure which will give you a profiling and a privacy of yourself to do the test, and store the data, use that data need basis when you go to a doctor to consult him? How do you really create that kind of a platform and an ecosystem? Now, the same one, what I just showing one file back, if I look at a little more lenser view of it, you have this kind of a structure, which is you have a package substrate, you have a 2 die attached to each other, facing each other, and they pop memories and structure. So this is actually a 3D stacking where you try to stack multiple die together. It multiple means this is simply a structure. The first product when we launched the commercial product first in the whole industry in 2019, where an active 2 die attached to each other and was tapped out successfully and commercially launched. This is a path-breaking technology for the whole industry to take it further. And now if you see it, it is being adopted by multiple companies, including the competitions, to do that. So the innovations is not a in a monopoly of anybody. It is actually a community health for all the entire ecosystem, and the industry, academia, all need to catch hand to each other to solve these challenges and opportunities. Now, the same cartoons I just draw to show you that when you try to take a bigger scales, not necessarily one die, you can do a multiple bottom die, you can put a multiple top die, they can connect to each other, create a connectivities. So you can imagine what you want to do and develop the technology around it. And if you just wanted to think about a pointed solution from A to B, you will only go to A to B. And if you imagine something bigger, you can do something bigger. I'm just quoting from, Einstein, his famous quote to be, used. So the whole message is there. The technology will evolve over a period of time. How do you leverage and take a benefit out of it to create the biomedical instrumentation is the questions, and everybody need to think about it, including the academia and industry. So now, if I look at these title lens in terms of engineering point of view, it's easier said than done. Each of the SOC, when you tape out, it costs to all the design houses millions of dollars. And how do you really make sure that before the design, you create a tool flow methodology where you can actually test the structure, the 3D structure what we have talked about, how before I tape in, before I manufacture, I know that my design going to work. You have to have a industry developed tool. EDA companies are developing their tool. How the design houses are also have their inbuilt tool wherever there is a gap in the EDA community, or they don't find a commercial values of investing and developing that tool. Let's say in case of a 3D IC first phase, the industry tools were maturing. They were not sure whether they will invest or not. So as a design house, you have to also have a muscle power and money power to develop those tools what you need on top of the industry tool to validate the whole structure and go about it. So in this case, I was just trying to show that when these two dies we are swinging on top of each other, how do you really create and do a simulations to show this, where is the voltage drop, or which you call as an IR drop is more. If you see this is the red spot where the IR drop was more at the early phase of the design. I just saw the cartoon to show that all of you, saying that you need to be extremely careful, not just by designing, you need to make sure that tool flow methodology for the EDA tools are available to make sure that you are able to articulate the physical phenomenon upfront, correlate that in a test chip, and develop this device as step out. So that way you can get a predictability. As an engineer, our job is to make sure that we create a product which is predictable and working with a high probability. You still can make a mistake. That's a different question. But by design, it should work. That's the intent and the design thinking all of us needed. And this is a huge area where the multi-physics engines are needed. It can work by one part. You need to make sure that thermal engineers coming into picture, the material science peoples are coming into picture, the vibration analysis peoples are coming into picture, civil engineers coming into pictures, and creating an end-to-end solution kind of a thing. So multidisciplinary research is the need of the hour, where you can do something tangible, benefit translating to the product kind of thing. And it does happen, by the way, today as well, but it need to be done more and more. So this cartoon again is the same infographics I put together to see the multiple kind of problems you found out doing a concurrent analysis. When the bottom die, let's say you are running some DDR transaction, the top die you are doing some kind of a CPU running at 4.5 gigahertz, 6 gigahertz, how they will interact to each other, how this power delivery, thermals, electromagnetic interference to each other will impact the devices. That needs the details 3D modeling of analysis by the tool, and making sure that the devices is actually working very nice. So in a summary, what you need to make sure that the thermal analysis, reliability, stability, yield modeling, cost benefit, and ROI before you defining a product of 3D or 2.5D, or you can think about the next generations where you can do a multiple chip together kind of a thing. You may have seen a lot of devices are coming out from the different company where one chip, which was earlier a concept of talking that I will take a wafer, cut into slices and take a small chip. Now the whole wafer is becoming a one chip because the complexities of the design is increasing. You need more and more number of compute power to do the things of operation. How can you really leverage and take that and do an academic research and industrial research to make that a commercially viable product kind of thing? So if you see the where we are going next 5 to 10 years down the line, this is an interesting infographics. Today we are here. We are trying to do mostly full diet, one top of each other kind of a stacking. Some companies are doing IP over IP, core over core. Then it will be going a macro over macro. It will be going over kind of a transistor over a transistor. So even an inverter you wanted to design where an NMOS and PMOS can be part of the two different die and you can connect them. So that kind of a slicing is and sandwiching. It's kind of a, you slice a potato in an n number of places you want and you place them in a manner where you can get the best structure out of it. And still they will talk to each other and you get into the picture. So that's where the industries are going. And I think over the next 5 years, it's going to be this space. And once we go there, think about this along with the research what MIT is doing in terms of carbon nanotube or single particle based transistors, we should be able to scaling down the whole size by at least 100x or even more. And this is actually a huge opportunities if you look at it, right? The market, as I was mentioning, market is the one thing which drive the innovations. The need of the people actually drive the innovations. And many times people don't know what is the need is. As an academic community, it's your responsibility to create that need and awareness within the communities to make sure which areas they should invest and make sure that they get a quality return out of it. Return in the sense, return for the mankind. I'm not talking about the dollars. So this cartoon is to show that the AI, artificial intelligence, we talked about the 3D technology so far. Now, as I mentioned, 3D technology along with the AI and ML to transform the medical instrumentation world. See, AI and ML is the another part where you see the year and our progress is significant, and it is going to be even further. So what does it mean to the researchers? So AI and ML can be implemented in a software, can be implemented in a hardware. If you make it in hardware, like any other cases, it become much more faster and efficient. That's why you may be hearing a lot of the companies that creating the computing environment which is more friendly for the AI based design, where some of the operations can be done in the hardware levels and it is much faster over there. That's why you see a lot of accelerator coming into the game. And again, there is no one fit solutions there. There are certain applications where it works better for the CPU, certain applications work for the GPU, certain applications work for a special purpose hardware. So you will be seeing a trend where a mammoth computing platform in combination of all of this is going to exist in the industry. And maybe we'll find out some other structure a couple of years down the line, which is in combination of that, but that's a far-reaching statement. And those innovations is going to change the paradigm of the biomedical instrumentation devices, starting from the genome sequencing, starting from the individualistic medicines. What medicines a person's work? How do I do the, create an antibiotic saying that for this particular person, this particular antibiotic is the best one. Today we do based on the blood culture best. How can we do it the whole body bacteria analysis and can do that kind of a thing? Using the, or how can we look at our DNAs and find out a pattern within that and saying that this person's most likely this particular bacteria is more there in their body and this particular drug is going to be working more. So we need to go beyond what we are trying to do it today to keep the innovations going. Yeah, this is actually another part of it, right? When you are driving a car, there are many times the accident happens. There are many cases you see the heart attack happening when people are running on a car. And how do you really get the data when you are driving? How do you control your nerve when you are driving? And you see there's a lot of communications happening when you are coming from your car to the multiple places. How do you really create a kind of a protocol, secure protocol, as well as the data monitoring, so it can go to the nearest health center and you get all the benefit. In terms of accidents, you get a benefit over there. So the whole communications, the real-time communications plays a significant role. And that's why the 5G network, if you look at the title of the topics, is another critical piece of information which you need to transform ourselves to the 100x scale or even beyond that. So we talked about the technology, the VLSI technology, we talked about the AI/ML, and we talked about how this 5G network can come and help the whole ecosystem. And another piece of information is we are all hearing about the cloud. The cloud need to be available and accessible to each and every individual to do their compute, to make their life better and easier. And we are an Intel, we are committed to this. So if you look at it, the compute is essentially a computing engine, CPU, GPUs, and data analytics, which basically means the data, what is coming to the computing platform, it analyze the data and give you some meaningful insight. So cloud is basically, and then delivery is to your Facebook, you are using Twitter, you are using, tons of applications, YouTube and all, which creates the data analytics. And the background of it, there's a storage. And the storage demand also is increasing day by day. So if you look at it, I think where the research need to be done, how can I get the data at most secured manner and infer the data in the data analytics? So the whole gaming of biomedical instrumentation is going to transform in a manner where it is going to be on time, real time, the data collections. And this cartoon is just to as a backbone. You can have it in an age. You may be thinking this cloud can be sitting in somewhere else. Cloud can be a small cloud, which we call as an edge, sitting on your platform. Let's say hospital. You're going to Manipal Hospital. Manipal Hospital can have their own cloud, a small cloud sitting at their campus, which will do all the compute, and then upload the data which is needed to the network, the other Manipal network, hospital network. So you can create a kind of a classifications over there, which can actually create a lot of help to these communities. So this actually are talking about how the things can be applicable when you have this kind of a huge computing power and the VLSI technologies to do the bacteria analysis, which is another kind of a stuff, and you create a molecule which actually can be helpful to kill a particular kind of a bacteria based on your body's compositions, not based on the average study. Today, the medical treatment happened based on the average study, because such a rapid way of creating the drug, such a rapid way of creating molecules was not possible. Now in future, a lot of research is happening. How do you really create that? Maybe it will come after 10 or 20 years, but that groundbreaking work need to start now to make that happen. So the key challenges in biomedical technologies are safety first. Second is there has to be a lower grades, energy cost. The remote location should be able to available to everybody inside the smallest village, maybe in some national park inside the small remote village. There also people should be able to leverage this. And how do you automate the whole stuff? So the data which is coming in a remote village, coming to the city doctors, and they can prescribe the drugs and get the same kind of a treatment what a person sitting in the hospital is getting. That's an important automations of islands of automations are needed. And the value chain gap. Today, a lot of innovation doesn't happen because people don't see the value. So technology must keep in mind that it must produce as a value to the people directly or indirectly, then the technology will flourish by itself. So that's the another piece of practical information we are trying to talk about. Now, why 5G is beneficial? 5G is talking about the latency. So if you are looking about compared to 4G to 5G, you should get a much more lower latency from 50 millisecond to 1 millisecond. So you will get much more faster connections, and you need that. You can't afford to wait for the reports to come out. You think about the situations. If this fast it comes, the moment you walk into an MRI rooms, once your data is come with AI and ML, the analysis is being done. It come to the doctor's room, and he get a reports AI-based reporting and the photograph. Now he can correlate. Maybe over a period of time, and as you know, the beauty of the AI and ML algorithm is that they learn it by himself. Initially, it will make some mistakes, but over a period of time, the AI will give you 99.9% kind of an accuracy. And even doctor accuracy also, if you think about, today also we go for a second opinion. How many times the doctor also makes human mistakes? I'm not, they're great doing the great job, but because this is the nature of the job that they will make some mistakes. So this can help or rethink their thinking process that yes, I'm getting some kind of a side help which I can leverage too. So net, I think this is a great technology which can help the people and the human being. Now at Intel, we have created a kind of a computing environment which can be used and leveraged based on our core. We have a Xeon core for the high performance computing. We have the server class computing, the Xeon. Then we have a big core, Atom core, and I have created a platform, the whole ecosystem, where you can do a rapid prototyping and use those technology which are using for industrial automations, can be used for the biomedical monitoring and an instrumentation purpose. So we are committed in Intel to make sure that we contribute to the society to create the biomedical industries safer and better in terms of providing the computing platform, in terms of the providing the software stack through our OpenVINO. Our next generation structures will come at some point of time. Again, this is no commitment. This is, I'm talking about purely from the aspirational goal point of view. So there will be a lot of innovations that are happening inside the company and in the industries, not just in Intel. Across the board, if you look at it, people are coming out and a lot of startups are working on this, leveraging the technology to see how can we get the meaningful information from an MRI report. How can we prevent that mass TB, tuberculosis disease, when just they go to and you can't have a TB specialist for every village kind of thing. Today, we all know this skew of the doctor ratio. So how can we really do that one for every village? Do a screening, upload the data, and it automatically will say that which peoples are having the TB and make it eliminate the TB disease from the society completely. So a lot of the research and the computing platforms are getting developed in Intel, and we are helping in the ecosystems to work together kind of a thing. So again, the next generations where we are trying to create an AI enabled computing platform, which we can put it in your premises. It's a cloud is a costly one, and it takes a larger throughput time. So you can create those infrastructure inside your campus, or maybe a couple of campus together partnering, or you can be also available in the all the 5G operator, Reliance, Jio, and all. So you can get there and get this computing help what you need. I mean, our focus is primarily to provide the computing need for the mankind, to create a digital, information age where the compute power is seamlessly provided at the lowest possible cost. Now, if you see today, what I was trying to talk about recently, if you look at the ARVO journals where it comes about, there is a certain kind of a disease which is extremely difficult to find out that is happening or not. One of this is the eye getting dried over a period of time. Now, the research shows that yes, those kind of disease also can be detected looking at the patterns of the eyes over a period of time. If you keep doing the scanning, maybe after every year or kind of a thing, you can find out the systematic patterns and see that whether any kind of a changes is happening in your eye in a structural manner, which may not be visible by today's technology. So what we really need to do, we are still far away from the innovations. Many times we talk, yeah, we have innovated enough. It's like kind of what else I'm going to do. If you think about the problem, that humongous amount of problem. Today's the computing environment, what the industry is producing is what best they can do. It has not reached to a state where we want it to be in humankind. Today, if you look at it, our human brain itself all of us still remember what breakfast we have taken. All of us remember yesterday what breakfast we have taken. Think about your memory power. You still remember which plate we have ate. We still remember what ingredient was there in the food. So and brain does that with a very minimum amount of power. And if you think about this data is being exchanged in terms of 100 billions of neurons. And between 100 billions of neurons, there is a neighbors and there is a connection. 100 trillions of connections and 200 calculation per second. So brain is an extremely efficient machine. It does the computation, whatever is minimum needed. It decide that. Now, such a computing platform and it's all doing at 70 millivolt kind of a voltage. Think about this. Today's all commercial applications stuff you see roughly about 350, 400 is the lowest possible voltage. Most of the main computing platform is a 1 volt, 600 millivolt, 700 millivolt and this kind of thing. So we are far away from where we want it to be. So the whole industry is this technology, the VLSI technology, still far away to go to match with the human brain what is trying to do it. Very smart. It is doing exactly what need to be done. It's not doing more than that, less than that, and it's doing it extremely low capacity and efficient. How do we mimic this structure and create a kind of an environment or a compute which can be far better than our brain does? And maybe go to the next generation. Sure. With that, I must thank the team at Intel, which is Joy, Noel, Usha, our group president, Sambit, Surya, VP, Anil, VP, and Naren, Wilfred, Arpan, Ajay, Rupesh, and the team for helping to preparing this material together. And I think my all colleagues, a big thank you for your time and giving me the opportunity. And I think we can take some questions if there is any.
Thank you very much, sir. Dear participant, any questions you can interact with Sajid. Sir, question inquiry from my side. I want to know about slide.
You want to know about, sorry?
Circuit slicing.
Oh, circuit slicing. Okay, that's interesting one. So when you talk about the circuit slicing, what does it mean? That basically means one transistors you do it in one of the chiplets or a SoC, and other part you fabricate into the another SoC, and you create a kind of a structure where they will connect to each other seamlessly. So if you see this cartoon where I'm trying to show through this one, where you can this one, where you can do the half of the transistor in the bottom die, the cartoon what you're showing, and half of the transistor you do it at the top die, and between them there will be micro bump, just a metal connector to connect to each other. That way, you don't need to think how I will connect. Let's say if the space is very tiny, think about there could be some of these inside our this all arteries and smaller arteries or some neuron cases, which is very tiny in nature. It has a certain dimensions where it can only fit. And I cannot fit this into the horizontal directions, but I have a space there to put into vertically on top of each other, which is extremely sensitive in terms of the area constraints. There, you can think about the circuitry to be designed in a safe way you wanted to do by slicing the technology into a multiple chiplets, stacking on top of each other, and still you make it work. That's what is calling about the circuit slicing, where you actually dividing the feature between the two dies seamlessly, and it still works. If you look at this cartoon, what I'm talking about, let's say half of the transistors you're putting it over there, half you are putting over there, and through the micro bump, which is the connecting between these two die, you actually make the connection between them. That's what is the circuit slicing to think about.
Thank you, sir. I think some questions are in the chat window, sir.
Yeah, maybe you can read for me. I
Yeah.
can take it up also.
How can we adopt VLSI in medical? First question.
Sorry, what is the question?
How we can adopt VLSI in biomedical, sir?
Okay, it depends on the type of applications, what biomedical you are looking at it. Biomedical is a vast topics, right? So if you are thinking about implanting a device inside your brain to enhance the memory capacity, that's the one of the applications where you take a memory chip and bunch of uh, sensors which connect to your brains and neurons, and you apply that. That can be one way of doing it. This is actually sitting inside the body. Similarly, you can have some instruments can innovate, which you can put inside the body, which will continuously monitor some of the parameters of the body. Those are the monitoring system or a support system you can think about. There are biomedical instruments which basically does the testing through the sensor. So you do your the blood testings and the n number of testings where you can get those done using the VLSI, a very small, impactful, a small low-cost SoC, put inside and use and throw. It improve your safety as well, right? Today it is not possible because cost coming into picture in many places. 30 rupees test, you getting it done, and if you put it, cost may be becoming 100 rupees, so people cannot afford it. Those questions are coming into picture. So even in number, or if you wanted to do the genome sequencing, it's also a biomedical machine where you put your sample inside a kind of the way you do the sugar testing, and that instrument will tell you, attached to your laptop, get the genome sequencing data. So you have a tons of applications where you can use the VLSI technology and the computational power. So wherever you see there is a need of computational power with a very small feature size, and you can use this VLSI technology for those applications. Any other question in the chat box?
Yes, sir. Yes, sir. So difference between, I think, GPU as well as NPU, sir.
Okay.
GPU
So,
versus NPU.
okay, so GPU, all of us know this is actually a the general purpose computing. So if you can think about this way, right, and basically today, if you look at the classification, today people are calling about all XPU. They are not calling about the CPU, NPU, GPU. The new nomenclature coming up XPU. Because what happening, right? Some applications are working, it's a numerical processors or a numeric processor. You take it. Some of these cases, like an NPU, working in a specific environment better. Why is it happening? Because if you remember the earlier 8 architecture where all the cores, atom core or a big core or the Xeon core, they were inherently earlier were carrying the instruction set which was used for a regular multiplications, divisions, subtractions, those accumulations kind of a thing. Now the general purpose computing, it uses a little different structure to be more broader view of it. And when you try to do this kind of a lot of neural network kind of a network NPU, you are trying to do this kind of a lot of let's say algorithms, which is GNN or RNN, those kind of algorithms. You have put it inside the computer itself to fast the process. Now the same workload you can run in any of the platform by compromising on the speed of it. It may take a lot of time or the accuracy. So the question here is, you can choose the kind of platform based on the workload that you get and a benefit you see. That the kind of a computing. And today's, if you see, a lot of people are talking about the XPU, which basically means a X is, and you can do a kind of an application based processors. While general application is very nice, you can get it done by the regular processor itself. You don't need anything extra help.
So next question, sir. Recent area of research in NOC, network on chip.
Yeah, so a lot of people are working on the area how you can reduce the conflict resolution, fast, better. How do you make it power efficient? Today, the NOC also take about 30%, 25-30% of power during that in the while it is a transactional part of it. So how do you really build the utilities to reduce the power significantly is the one of the way to look at it or think through. So it's a kind of a evolving field, I would say, which is changing. And you can work about how do you make it more power efficient, how do you do the better conflict resolution and seamless integration, because multiple SOCs, if you do it, knock areas people are working, how can you port it very fast so that you can do a faster time to market? These are the 3 areas to look at it. Any other questions?
Yes,
Yeah,
sir.
what happens?
Please relate for speech to angiograph, ECG, EEG with finite 7 mm. FinFET 7 mm. Sorry.
Yeah, so if you look at it, right, there are 2 parts of it, right? When you try to do the FinFET 7 mm, what benefit you get? You get the benefit in terms of the power, and you get a benefit in terms of the performance, right? These are the 2 benefit when you change the technology to technology. And this actually is a great stuff. Now, when you are trying to do this technology migrations, you mostly do each of the devices to get a better power and performance, and cost also reduces because of the wafer space you get reduced, right? So when you use the 7 FinFET, you get those benefit into the equations, and you decide based on the time you want to market and the technology to be ready, so that you decide the technology to be coming across, right?
Next question, sir. Any current research going on integration of computer architecture NOC in biomedical field?
Sorry, what is this question? Any
current research going on integration of computer architecture network on chip in biomedical field?
Yes, I mean, there are a lot of people are doing the research, academic community, saying that in biomedical workload, certain workload, how the NOC can be much more beneficial. So that it's question of prioritization or customizations. So people who are generally creating a general purpose computer, that may not be doing it, but people who are doing it for the other purpose, they can use it, right? So general purpose computing wise, they are not focusing on this, but people who are making a custom silicons, they are focusing on it.
Next question, sir. Can VLSI architecture be developed for AI or ML algorithm?
Yes, if you see today, a lot of companies are doing the accelerator for AI and algorithms to be part of that AI enable instruction. They are not putting the all algorithms there as such. So when you have a n number of levels of computations, those computations, platforms are built. If you go and search Movidius or Havana Lab, those are our, brand product. And also the NVIDIA also has their own product. So everybody has their kind of a silicon where those instructions are natively embedded inside.
Thank you very much, sir.
Hey, thank you. Thanks a lot, Professor, for inviting. And it was a lovely interacting with all of you. Thank you so much. And let me conclude by saying a happy Teachers' Day to you, Professor, and the all professors and the teaching community here. Thank you.
Thank you once again, sir. Now I would request Dr. Baira Reddy sir to give vote of thanks.
Thank you. This is such a prayer that cannot be seen or touched. It must be felt like art. I feel honored and civilized to get an opportunity to propose thanks on this event by 2 weeks
Biomedical Applications. On behalf of EC Department, BIT, convey deep regards and hearty thanks to Dr. A.M. Ashpat, Principal, BIT, for his support and encouragement. Dr. J. Prakash, Vice Principal, BIT, for his regular support us, and Dr. Professor L. M. Patnaik, Adjunct Professor and Advisor for Technical and R&D Center, BIT. Thank you. I am also thankful to the keynote speaker, Biswajit Sir, for his gracious time and presence to give great advice on VLSI. Thank you, sir. Today, my words are not enough to express the gratitude to Rajya Vakilera Sangha and Bangalore Institute of Technology. Thank you. I would like to thank you, our HOD, Dr. Hemant Kumar, and Dr. Vijay Prakash, PG Coordinator, their guidance and support to conduct this event. Thank you, sir. I am very much thankful to all our teaching and non-teaching staff and HODs of all departments, BIT, and participants in this event. Okay. And also I am very much thankful to the sponsoring agencies for their support, like IEEE Student Chapter and CAS team. Thank you, sir. Thank you, one and all.
Okay, sir, ma'am.
Thank you very much, sir. Now I would request Professor Gahan to read the next speaker biodata.
Thank you, ma'am. Satyan Balaji, engineering manager, ASIC design in NVIDIA. Shri Satyan Balaji has over 20 years of experience in VLSI front-end design for systems spanning communications, multimedia, networking, accelerators, and SoC. He's an engineering manager at NVIDIA Graphics, Bangalore, leading a team of designers and architects working on input-output interconnect protocols. He holds a bachelor's degree with gold medal in electrical and electronics engineering from the PSG College of Technology, University, Coimbatore. He has taken several leadership roles in the IEEE student branch. He has chaired the IEEE Gold Affinity Group Bangalore, the Best Gold Affinity Group Award for Art and in 2004. He is an amateur radio enthusiast and likes to read history and economics besides science and technology. Sir, dear sir, we warmly welcome you for 2 weeks faculty development program. Thank you.
Thank you. Am I audible? Is it fine? Hello? Hello, am I audible?
Yes, sir.
Okay. Thank you all for inviting me to this event. It's my honor to be part of this event, especially on this special day. Happy Teachers Day to one and all present here. I'm what I am today because of my teachers. So thanks for this opportunity, Dr. Jindal. So my talk is going to be about recent trends in VLSI design. So this will be slightly different from what Dr. Patra spoke a little while ago. So VLSI technology deals with the hardware part, the fabrication part, and the design deals with what we do in the front-end design and what kind of architectures that we use and various other parameters that we try to optimize in the process. So again, like power optimization does happen at the fabrication side also, but this is something that there are other parameters that we design considerations that we make at the time of design. So I'm going to discuss some of those. So at the outset, when Dr. Jalaja spoke to me about this conference, like I was like just trying to think through. Like sometimes we miss out like what the work we are doing about this thing. So I was trying to think through like what are the VLSI applications that we have for biomedical, what are the applications, biomedical applications of VLSI design. So on careful introspection, I see that today the battle is being fought at the compute front. Like we are, there is one aspect of biomedical application, which is the transducers, sensors, and actuators. Setting that aside, like there is another aspect, which is the compute, where like as Dr. Patra pointed out, genome sequencing or analyzing, like say we get CT scan reports, like reinforcing what the doctor infers from a CT scan report. So these are some of the things that are being enabled by AI and ML, and NVIDIA is at the forefront of AI. So let me just start with, and also there are multiple other computational tasks which are getting accelerated through NVIDIA's GPU. So let me give a quick overview of those. Let me start with this video. Please let me know if the video plays fine. I can repeat it, or we can just work it out.
The video.
Okay. Yeah, let me just let it buffer again. Yeah.
Visible, sir.
Yeah. Okay. It's not visible.
The
Hello?
video is visible.
What
Only
about now?
audio is. No, sir.
Okay.
Sir,
Yeah. So
audio is.
okay. What about my slides? Are they visible now?
Only your face is visible, sir.
I'm sharing this slides actually. Just a moment.
Share your slides, sir.
Yeah. Is the slide visible now?
Yes, sir. Yes, sir.
Okay. Probably let me just replay that. Let me know if there is any problem. I'm sorry, like I think technology has its own disadvantages.
Yes, sir.
Is it visible now?
Yes, sir. Visible. But audio is the problem once again.
ಡೈರೆಕ್ಷನ್ ಕೊಡಿ ಎಲ್ಲಿ ಬರುತ್ತೆ ಶೇರ್ ಕಂಟೆಂಟ್
ಶೇರ್ ಮೇಲೆ ಕ್ಲಿಕ್ ಮಾಡ್ಬಿಟ್ಟು ಶೇರ್ ಸಿಸ್ಟಮ್ ಕಂಪ್ಯೂಟರ್ ಆಡಿಯೋ ಅಂತ ಇದೆ ಅದು ಕ್ಲಿಕ್ ಮಾಡಬೇಕು.
Sir?
Yeah.
You're supposed to click on share and computer audio.
Okay. Yeah.
Click on share and after that select computer audio.
Okay. Okay. That's okay. Let me just.
Share your screen, sir.
Yeah, I'm sharing my screen actually. Oh, okay. Just a moment. Just a moment. I think I got the problem. Okay, so what I wanted to highlight with this video was that, as you might have seen with the our agenda also, the entire first week is kind of dominated by topics from AI and ML. So, like AI and ML in healthcare is also like one of the critical aspects, and that is becoming like one of the hottest topics of research as well. And NVIDIA has a suite of tools called, which is bundled as a toolkit called Clara, and that actually gives a lot of innovative solutions, like opportunity to innovate through that toolkit. So let me try to play the video later, but I'll talk over like what is the hardware challenges like that is involved in creating such AI applications. So what you see on the right-hand side is the NVIDIA Hopper. We call it the GH100, Hopper 100 chip. So this is just being released to customers right now. This chip, to put things in perspective, this has about 80 billion transistors. So if you want to put this in perspective, like it's roughly about 10 transistors for every person on this earth. And this chip can compute about 4,000 T-flops, which is roughly about like 400 times more powerful than the most powerful desktop or a laptop PC that is available today. That's the capability of this one chip or one board which I'm talking about. So these are the VLSI devices, or these are the VLSI, these are the chips that are driving the forefront of AI and ML today. And coming to the one on the right hand side, like this is super chip, the Grace Hopper super chip, where we have a GPU. This is the same as what we see in the left hand side, where is the Hopper CPU, GPU, and a Grace CPU, both stacked on a single board. And this super chip goes into servers, and multiple of this super chip builds a supercomputer. And this expedites a lot of these computation that we do in AI and ML today. To put like a genome, take the case of genome sequencing from days or even hours, from years of effort, it has boiled down to few minutes. And as Dr. Patra pointed out, democratizing tools like genome sequencing is like being enabled by AI and ML. When we're building these complex chips, like there are multiple things under consideration. Some of the technology aspects, the VLSI technology aspects, I think Dr. Patra already covered, and I'm going to cover the design aspects here. So let us see what are the design aspects, the major design aspects. There are multiple other things. I'm just considering the top 4 design aspects that we typically consider. So they are the size, the cost, safety, and security. So let us go over it one by one. So size challenges. So we all might have read in books that there used to be a law similar to the Moore's law called Dennard scaling. Like Dennard scaling is nothing but it's not a law per se, but then what it says is the CMOS transistor scale in size and with constant power density. The constant power density is the most important factor here. So what it says is like whenever we scale the transistors, we also need to reduce and increase the number of transistors in a chip. You also need to reduce the voltage or the power and thereby the voltage that can power the transistors. So why the Dennard scaling has slowed down? That's obvious, like because of physics, like we have this reverse bias voltage and nothing can, like we have very little options to fully eliminate that. So what happened with the going away of Dennard scaling was, there is an important metric that we use to build these chips and thereby the systems. That is called the perf, or the performance per watt. So the performance per watt used to scale with the Dennard scaling, and now with the Dennard scaling gone, it requires architectural changes. When I say architectural changes, like we are used to having a CPU, like or we are used to having a server which has an x86 processor, but albeit just a processor, nothing more than that. But now the processor alone is not going to suffice. And that's exactly what Dr. Patra also referred in his previous talk, that we are going into a domain of XPUs, or something like a GPU, which is a graphics processing unit, a DPU, which is a data processing unit. So all these are hardware accelerators. So the size challenges like pose make us to look for alternative architectural solutions, and that takes us to hardware accelerators. So a picture I've shown here on the right is the picture of a DPU. So DPU may hitherto be unknown to most of the people, but it is nothing but a data processing unit. It's more like a marketing jargon, I would say. But what it actually does is, this sits in the network interface card. Like the picture which is blurred in the background is that it's in a network interface card. A part of this DPU is a network interface card. On top of it, it has got acceleration engines, programmable ARM cores for doing some computation, and a PCI for interconnectivity. Like what do these acceleration engines do? Like there are multiple network operations that are being carried forward. Like of course, when we say a system is not just processing. The system is also interconnect. Like a processor, when it computes data, it has to take the data. The data has to be taken and stored into a storage or a storage network, and it has to, and sometimes like these days, like the data centers are becoming so complex that the processors need to talk among themselves. So that is where the network comes into picture, and accelerating some of the network functions like encryption or a table lookup. So these are some of the things that the DPU does more efficiently. And what it does is it takes out the load out of the core processor or the x86 processor. So, by the way, I just want to do a quick check. Like, are the slides visible and you don't have any problem at this point? Are we good to go? Hello. Am I audible?
Yes, sir.
Okay.
Yes, sir.
Okay. Thank you. Thank you very much. So at any point in time, I'm also looking at the chat window on another monitor. So any point in time, feel free to drop a question. So we can have an interactive session. So these are the size challenges that we talked about. So now what is happening? Like what are the solutions? Like the solutions are like we try to reduce the power of the design. So we have a bunch of techniques, like certain techniques we may not explore previously, because so when something comes for free, when you don't have to put in that extra effort, like people typically don't tend to burn that because it comes with more cost. But then now that we are gated by all these technology limitations, like we are going to reduce the power, like make it lower power so that we can compact more transistors. As I told you, the power density is a more critical thing. So reducing the power like makes it more compact. But not all applications we can have low power. Like not all applications can be low power. Like there are some applications, especially in biomedical, where power cannot be reduced beyond the threshold at the cost of reliability. The next comes parallel design. So we might have all heard about multi-core processors like the typical i5, i7, i9. So all these numbers stand for like how many cores are going to be there in the processor. But what is the limitation there? Like the multi-core processor, but just by throwing in more number of cores, can we achieve what we'll be able to achieve? The restriction comes there in the form of what is called the Amdahl's law. When we say that we can put in multiple cores, like what happens is like we need to also segment our task. For example, we are doing a matrix multiplication. Say a 4x4 matrix multiplication, there will be finite number of multiply and accumulate operations. So when we say a multiply operation, the multiply operations can all be done parallelly. So we can probably, I'm just giving an example, but this is something which is not done in a normal 16 core processor. I'm just taking an example so that we can all be on the same page. So like we can do a multiply parallelly, but then for adding, like again, it becomes a bottleneck. So that is what the Amdahl's law says. Like Amdahl's law says that when we parallelize the design by adding multiple cores, like the process which takes the maximum time becomes the gating factor, and that determines the overall efficiency of the parallelism. Beyond this, we have other techniques like efficient memory and paging and caching. So when I say paging and caching, it's a topic on its own. Like this relates more to computer architecture. The more number of times we access the DDR memory or the HBM, these days we have what is called the HBM memory, which can be stacked onto the chip. So the more accesses that we make to these memories, like the more the latency is going to incur, and lesser number of computations are going to be provided per second. So how to improve the paging and caching techniques? And then the locality, the spatial and the temporal locality. So when we fetch the data, can we fetch a little bit more data from the same page in the DDR? Like a DDR memory is organized in terms of pages. So if I fetch the data from the DDR, like for a particular design, am I making the best use of the data that I'm fetching? Or when we read a page from the DDR, are we making the best use of it? Can we store the data in such a way in the DDR such that the reads and writes can be optimized? So all these 4 topics which I've listed down, they are all active topics of research as well. There are multiple research going on in these fields, especially like topics like parallelism, where multi-core getting the best efficiency of the parallel designs, and also the efficient memory paging and caching techniques. So the solution boils down to hardware acceleration, as I pointed out. Like we have accelerators like GPU, FPGAs, and network accelerators like DPUs. So I just put a chart here, like to give a perspective of where things stand with respect to acceleration. So from the 80s, like if you see, like until hardware acceleration started as hardware acceleration started becoming a commonplace thing. Like we had a single thread performance, which was slowly ramping, and then the multi-thread performance was slightly above that, which was like increasing at a pace of like 1.5x to 1.1x per year. But then somewhere in the 2000s, accelerated computing started gaining more traction. That is, for example, using GPUs. Accelerated computing, so to speak, I can say that it started with NVIDIA GPU because of the availability of the CUDA programming language. And then this is the kind of acceleration that the accelerated computing has provided in the last 10 plus years. Whereas the single thread performance of the traditional CPUs is kind of plateauing, the accelerated computing is still waiting to reach that kind of a plateau. Beyond the accelerated computing, we also have what is known as a scale up and scale out. Like when the chip that I showed in the first slide, that is the Hopper 100 chip, that is just a single chip. Like now, what if we can create a cluster of those chips and use it in our application? So these are the clusters, and at NVIDIA, we make these clusters and we call it the DGX. The DGX, and now we are in the second generation, DGX2, will soon be in the third generation, DGX3. So these are the scale out applications where we can, multiple of these clusters can be connected and we can create almost a supercomputer. And these can be like hosted in the cloud, and renting them comes at a fraction of a cost. And then comes what is known as a machine learning. So when I say today, NVIDIA is using something, an interesting technique. So if you have been using, I mean, if you have a gamer, you might know that number of frames per second, like the number of frames that are displayed per second is the most critical parameter. And displaying more number of frames per second involves more computation. But can we relate? But the video is not going to have too many changes. There is a contextual information from the previous frame that is already present in the next frame. I'm sure, like if you have gone through the video encoders and decoding standards or the video coding standards, like they make use of the same technique. So we have a machine learning algorithm which learns what or how the frames change, or what kind of background that the game is using, and what kind of motion is being used in the game. It learns that, and then it operates and provides us a greater FPS without the actual video buffers having to process the data at that speed. So that is where the machine learning is going to further provide multi-million time speed up in our computation power. We are actually at this juncture now, and this is also speeding up without, and we are not seeing a plateau on this yet. Any questions at this time? So I think like there was a question in the previous session about how do we okay, I think we can answer them. Fine. Yeah, there was one question about VLSI architectures to be developed for AI and ML. I think Gupta NPS, like they had asked. So like when I come to a GPU, like in a GPU, we have specialized architectures called the tensor cores. A tensor cores are nothing but specialized hardware that we use for doing matrix multiplication. If you have taken the machine learning or AI courses, you might recognize that the matrix multiplication is a basic math behind all these algorithms. So the tensor core is a core that we designed for accelerating matrix multiplications, and those are embedded in the NVIDIA GPUs. Okay, please elaborate on paging and caching. When I say paging and caching, like okay, when I said talked about clusters, like all these for a typical genome sequencing kind of application, the chip that I showed earlier, like the GH100, it's not going to be used in isolation. It's going to be used along with multiple other such cards, and all these cards are going to be plugged into a bigger pod, which we call it a pod, pod, which we call it a DGX pod. And depending on the some companies' requirements, certain labs they purchase multiple such pods and interconnect them, and then like those pods are interconnected through the smart NICs, and it becomes a single big supercomputer. So when I say efficient paging and caching, the chips which are on a single pod, they tend to have a unified memory architecture. So they view the entire memory or their local main memory in a single unified way. That is called a NUMA, NUMA. And how each of these chips are going to take the data from that unified memory and cache them locally in their local caches is what I refer to as paging and caching. There are multiple techniques, and still these techniques are not matching up to some of these parallel algorithms that we are having today. So yeah, that's why I said like there are a lot of research going on in this field, and it's mostly a computer architecture domain. That's about it. So I think, yeah, there is no more question. Okay, now let us come to the second aspect, the cost challenges. So I would probably make the statement that the Moore's law is dead now. So what was the Moore's law actually? It was like, I'm sure like everyone would have read some version of the Moore's law, but at the very least it says that the number of transistors in a chip doubles every year. So this worked perfectly until 28 nanometer. So till 28 nanometer, we were using what is known as a planar MOSFET and not a FinFET. So we were using a planar MOSFET till 28 nanometer, and beyond that 28 nanometer, there were some issues because of which we had to go to FinFET. I'll cover them in the next slides. So the cost per transistor, like if you see the Moore's law's corollary is that the cost per transistor also used to halve every 2 years. So the number of transistors doubled in a chip. The cost of the chip remains same. So the cost per transistor half every 2 years. But if you look at this chart, the 28 nanometer was a sweet spot where the cost per transistor dipped to the lowermost. And since then, it has started increasing. Now, if you look at different literatures, you may get different opinion. But what I'm projecting here is from the international business strategies. This actually refers to the total cost of making a chip. Like the total cost of manufacturing the die per se may not exactly match this graph, but then the testing cost and then the packages. So all these things have become more complicated, and the overall cost of a chip amortized to transistors, like they are showing an increasing trend since 28 nanometer. So that is where we need to differentiate what happened there. So till 28 nanometer, as I already told, like we used what is called the bulk or the planar MOSFET, but the planar MOSFET ran into multiple short channel effects. Let me have a slide, go to this slide. So this was the planar MOSFET. So we just had the source and the drain and then gate on top of it. This worked perfectly fine. But if you see the area of the gate area over the channel, as a size shrinks, the gate is having the gate starts having lesser and lesser control over the channel, and because of which we start having this short channel effects. When I say short channel effects, what could it cause? Like there is something called the drain induced barrier lowering, and because of which, like this transistors tend to punch through, and a punch through typically damages the transistor, and that's going to be take a toll on the reliability. Though initially testing the chip may work perfectly fine, but going ahead, like within a short period of time, the chip is going to fail. That's a reliability issue. So the industry moved to what is called the FinFET. So what happened is, like the fin is raised. It's raised from the substrate. This is the normal substrate. It's a raised fin, and then now the gate is designed on top of this. If you see this diagram, the gate is covering the 3 sides of this fin, the 2 sides and the top. So the entire gate width is now covering all these sides, the 2 into the height of the fin and plus the width of this fin. So for some applications or at some lower technology nodes, even this single fin is not going to suffice. So we go for what is known as a gate all-around technology, where we create multiple fins. Like each of them are source. They're going to be connected. Like each of them are source fins. They're going to connected, and these are all drains. They will be connected, and then the gate is fabricated in such a way that it fully encircles the fin. So now, if you look at this slide, like what has happened here, like we were having lesser number of masks for covering, for fabricating this planar MOSFET. But within the transistor, we are creating an apartment-like structure. Like Dr. Patra was saying, that when you don't know how to go horizontally, you grow vertically. So we are growing vertically at a transistor level. Like what Dr. Patra said was 3D stacking of the chiplets. But here we are talking of the 3D stacking of the channel area itself. So each of the chiplet is going to be having a transistor, which is going to have a channel which is stacked in a 3D fashion. Now, this kind of 3D stacking entails more number of masks. When I say mask, the fabrication mask, the photo mask, the etching mask, and so on, and that increases the cost of fabrication. So this is the cost challenge. So now this is a diagram which I think Dr. Patra has already discussed elaborately, but let me just tell you some more perspectives at what we do at the design level. So to overcome all these limitations, what we do is we design we create the entire design, or we split the entire design into chiplets. We can have an IO chiplet, the input output, or that kind of chiplet. We can have a compute chiplet. We can have an accelerator chiplet, and then put all these chiplets on this silicon interposer. And the silicon interposer is put on the package substrate, and this part, the first 3 layers, become a chip, and this chip is put on the circuit board. But now the challenge for the designers, like this part, I think like is more of a technology thing, but the challenge for the designers lies in how do we interconnect these 2 chiplets? When I say interconnect these 2 chiplets, it doesn't come for free. Like I need to have a specific interface. For example, like when we connect a DDR, it works seamlessly because DDR is a protocol. It knows, I mean, the processor knows how to fetch the data from the memory, and the traces are constructed accordingly, and there is a defined protocol. So we need to have a protocol for transfer of data from one chiplet to another chiplet, and that protocol needs to be very efficient. It should not happen that we spend more number of area for designing this protocol or for these protocol buffers. It so lands up that the benefits of using the chiplet goes away in the extra area incurred in designing this protocol. So NVIDIA uses this kind of a technique, and we have what is called the NVLink chip C2C. The C2C stands for the chip to chip, and we have a proprietary protocol called NVLink, which we use for connecting these chips. So these are the challenges in this part. And I think Dr. Patra briefly mentioned that there are some companies which even go to the extent of designing a wafer scale computer. There is a company called Cerebras. It's an interesting read. It's spelled as Cerebras, Cerebras. So they are a company which have come up with an AI chip, which is like where an entire wafer acts like a single chip. So that's an interesting read. So, okay, then comes the topic of heterogeneous chiplets. Now, this is the same as the previous diagram, where there are multiple chiplets which are being stacked on a single interposer, and this entire thing becomes a package, or this entire thing becomes a package or a chip. And this also shows the 3D stacking. Typically, we use the 3D stacking as Foveros technique that the Intel uses the Foveros technique. Many companies have different techniques. But what is more advantageous in this heterogeneous chiplet approach is that the IOs can be from a different technology. For example, a few slides ago, we discussed that the 28 nanometer was a sweet spot with respect to the fabrication, like the cost. So if, for example, some of these components don't have to be at the cutting edge of the technology, or some of these components don't require the latest process technology, they can still be at the older 28 nanometer. And the rest of them, like the compute ones, can be at the recent or the most latest technology. And all of these different chiplets from different technologies can be put on the single interposer, and we can create a chip out of it. And that's something which reduces the cost of the solutions. Okay, so we covered the first, we covered two of them, like the size and the cost. Any questions at this point? Okay, yeah, let me just proceed then. So the two aspects, design considerations that we saw till now are something which is not, some of the solutions are in the realm of the technology domain also. Like for example, size, like some of the solutions should come from the VLSI technology, where the fabrication setup, the fabrication methodology changes. But then, like, there are two other aspects which I want to discuss today, which are purely in the design domain. The first one is the safety. So when we say safety, like, let me just provide two instances. I will just put the references to these articles in the end, the last slide. You can have a look at it when you have the slide. So there was a very peculiar case with Toyota Camry. I think it was a 2005 model, and this happened somewhere in 2007. And Toyota Camry met with an accident. And there was some onboard diagnostics which said that, okay, like the person intended to push the accelerator, whereas like the person who survived in that car crash mentioned that, okay, the person didn't went to accelerate, but then the person applied the brakes, but then like the vehicle accelerated. So this investigation went on for a few years, and the investigating or consulting firm which investigated this failure, like finally found out that the Toyota software was not taking care of what is known as a bit flip, or a soft error which occurred in the chip that it was using. By the way, today's cars, they use like in excess of like 40 to at least 40 to 50 ECUs, or electronic control units, and they have like millions of lines of code of software written for them. And this particular case happened for Toyota. But the thing is, like for automotive, this is fine. But we are talking about what is going to go in a very much more critical application, like biomedical applications, where we can't afford to give such, where we can't have afford to have such room for error. So what we do for the soft errors. So let me actually go to the next slide. So when we take a product cycle, we have talk about the reliability of that product, like across three phases. Like in the first phase, or it's called the early infant mortality failure. Like we all know that, okay, when we buy a product, it comes with what is called the warranty. Like the warranty is given for a few years, and then there is something called guarantee, where the seller is like guaranteeing that, okay, there will be no failure at all, and he can take back the product. And in the case of warranty, the seller is willing to service the product. So in early infant mortality, like is when we send the chip. In the case of a VLSI, the early failures like show up mostly in the lab. Like they are stress test in the lab, and they show up mostly early in the lab. And very rarely, especially in consumer appliances, which are not like safety critical, like these faults tend to show up in the customer place, and that is why they are covered under what is called the guarantee. And then, like, there is a relatively long period of time where the observed rate of failure is going to be very low, or it's going to be flat. And during this time, the product failure is going to be much lesser. And then over a period of time, as a product wears out, like in the case of a chip, it could be because of electron migration and many other reasons, like the power controllers wear out because of the electron migration issues, or there are constant heating up, because of which, like I mean, the substrate starts breaking. So because of multiple reasons, the wear out failures start taking more, they start dominating this, and the failure rate increases over a period of time. Typically, the warranty lasts till this point, right, where the manufacturer knows that, okay, there is going to be lesser number of failures. In the case of, if you look at this graph, like there is going to be some constant random failures, like or errors, which are going to occur during this steady phase also. And any manufacturer or any equipment maker will try to elongate this period as much as possible to give a better quality to the consumer. So this is what we are talking about. And during the a long period, like typically what we encounter is called the soft errors. Like what are the kind of soft errors that we encounter? So there are high energy particles, or cosmic rays, which are like constantly entering the earth, and they can fall onto a chip, and which can toggle the a single bit in the chip. Then there are alpha particles, which are coming from the packaging materials. So what happens is, when a chip gets heated up, the packaging material starts emitting certain alpha particles. So this is not true with all the packaging materials. So certain more expensive packaging materials emit less alpha particles. So again, this becomes a cost metric. Then there are some aspects like noise, signal integrity, and crosstalk. How much ever design checks that we do at the time of chip design, certain amount of these things, these traits vary across the, over the period of time, and these start playing, these start showing up as soft errors. A classic example is the DRAM row hammer. Like it has been proved that in DRAM or DDR memory, like if we read a certain row continuously multiple times over and over, it has a tendency to affect the data which is stored in an adjacent row, which could be used as a targeted attack also. Like for example, you know what is stored in an adjacent row. It could be used as a targeted. It could be a mechanism for targeted attack, and that attack is called the row hammer attack. So these are some of the causes of bit flips, and bit flips are catastrophic. So I once happened to, there's a very famous VLSI personality in Bangalore. His name is Dr. Mahan Shetty. So he used to work, he used to be a scientist at TI for quite some time, and he founded his own company called Karmic, stands for Karnataka Microelectronics. He's no more now. But yeah, he was like a great teacher as well. Like so he used to tell an anecdotal evidence, like anecdotal story, that he was down with, I think he had a heart attack, and he was going to be operated, and he was taken to a operation theater, and he just saw the machine which he had designed during his TI days, and he then felt a little bit more relieved that, okay, he'd taken care of all the bit flips and all the reliability aspects of that machine. So those are the kind of catastrophic consequences that we can see if there are bit flips in biomedical instruments. So these are some things that need to be taken care of. The next two parameters we are talking about is the MTTF, the mean time to failure, and the MTBF, the mean time between failures. So can anyone tell me like where do we use this term MTBF? Like in electronics, we often use this term MTBF. It's often used in a particular in the context of a particular design or a particular solution. Can anyone just tell me where it is used? We use a technique in digital electronics to improve the MTBF or to increase the MTBF. So anyone? Perfect. Thanks, Girish. So it's a metastability. So we say that, okay, when we have a single flop and we are having a clock domain crossover, like the metastability can have a catastrophic consequence. But if we have a two-state synchronizer, what we said there is we are not completely eliminating the effect, but what we are saying is we improve the MTBF or we increase the mean time between the failures. That's why we have option of using a three-state synchronizer, where which increases the MTBF to way beyond the lifetime of a human being. So that is what we are talking about, like increasing the MTTF, MTBF. So these are some of the design aspects that we need to consider when making the safety requirements. Okay, some of the hardware solutions, like when we make day-to-day design considerations, like these are some of the hardware solutions that we put into the chip. Parity, like we try to protect all the important data assets with parity. Like parity is a simple concept, like check for either odd parity or even parity and add one more bit. Sometimes the parity is not sufficient. We go in for what is called the error correcting codes. So what is happening is, like when the technology node shrinks, the distance between the two memory cells in a SRAM or a DRAM, they are going to they're further reducing that even a single particle starts affecting more than one gate. So having a single bit error correction and double bit error detection kind of error correcting codes, they help more in this aspect. Then there are techniques like using radiation hardened flops. So where we say that, okay, the flop is not going to be affected by the radiation, but then this is but this comes with a cost, like area penalty. We also protect the instruction and data bus, like the instruction bus and the data bus are the critical digital assets on a processor. So if they are not protected, that could also cause that could also like we may lose fidelity because of that as well. So the instruction data buses are protected. Redundancy is another technique that we use, where we have two such designs running parallelly and make sure that both the results of both the designs match. If the data are not matching, that means something has happened and we immediately flag an error. Software assisted checks, like software can play an important role for mitigating some of these soft errors. Like for example, doing a read or immediately after writing into a register can ensure that, okay, the data which got written into the register is sane, or it's having high fidelity. And similarly, like repetitively reading the data once in a while in a loop, like once in a while going and reading the data and or the states of a or the states of a state machine. Like these are some of the things that software assisted checks can help. There are several standards related to safety. In fact, there are quite a few IoT standards, like which are stringent, but then the more stringent standards are coming from the automotive domain, where we have this ISO 26262, and they're talking about the different safety integrity levels. For automotive, like these safety integrity levels are defined as ASIL A, B, C, D. And similarly, like there are SIL A, B, C, D for other equipments. This is again another field of research, and more than research, there needs to be some organized study and standardization effort required for biomedical applications. So for biomedical applications today, we just generally tag them with IoT applications. We don't have a specific biomedical standard for safety. So this is something that can be that is an area of interest which needs to be worked upon. Okay, next comes the security. So I think like some speakers, like at least two of them I remember, like Professor Patnaik also was telling that, okay, how do I trust? Like I think he used the word trust. How do I trust that the transaction is coming from a particular, the correct person? So there are quite a few instances which I have just quoted in this slide, The most interesting of them I find is this Jeep Cherokee. Jeep is actually that Fiat Chrysler company which manufactures this Cherokee SUV. So this particular vehicle got hacked and remotely, like the hacker remotely hacked into this vehicle through its electronic. Just a moment. There is some power saving algorithm in this room also. Okay. So yeah, the hackers remotely hacked this Jeep or this vehicle using its entertainment systems. Like entertainment system has is all this Wi-Fi and all this LTE kind of connectivity, and the hackers found their way into it. They hacked the device. They made it stop. They were actually doing like more like a ethical hacking, because hacking is illegal. So they just wanted to prove the point that okay, a vehicle can be hacked. So they hacked this device, they made the engine stop, and then they started the engine all without the control of the driver. So this is a kind of security threat. I mean, this is the kind of era where we are at a security threat almost at every stage. So related to biomedical, there are multiple cases where like there have been cyber security hacks into patient monitoring systems to falsify the vital signs. Just imagine like this is like a Bond movie where somebody kills someone like a big shot, or someone like they just show that the person had a cardiac arrest and their own people kill the person. So these are some of the cyber security risks that we are in today. So what are the major ways in which, like I've just listed down the top few. Of course, there are multiple ways in which security can be compromised. I've just listed down the top few. First is a wiretap. Like someone has a physical access to the device, and they use a compromised device and then wiretap that. Wiretap is typically used, when we say wiretap is typically used for snooping the information, like taking the confidential information of a patient out or something. Then we have what is called the man in the middle attack. Like someone like can tap the wire, like they are tapping the data, and then they retransmit something falsified information. For example, a report says that okay, a person is having some XYZ problem, but then somebody in the middle taps the data and then retransmits saying that okay, the problem is not the problem is X1 Y1 Z1 and not XYZ. So that's like kind of another kind of an attack. The third kind of attack is a denial of service attack. A classic example of this denial of service happened some time ago in Germany. I think like a group hacked into the network of German hospital. They hacked all the devices. They made sure that none of the devices were in a usable state, and they even demanded a ransom in bitcoins. So this is a kind of damage that denial of service attack can cause. And I think in this case, like it was coming through a malware, like a malware injected through injected into the hospital's network. That gave the access to the that gave the access to the hackers, and the hackers were able to hold all the people at ransom. And the hospital was not able to take any new patients, and they had to shift the existing patients to a different hospital. One of the patients died. There was a big lawsuit. So all these things are real and present danger. So when we say threats, they can be sometimes they can be physical and sometimes they can be remote. As I said, like when you have, we can remotely hack a vehicle. Similarly, remotely we can hack into a network, and this can be the threat can be embedded. So what are some of the hardware security solutions that we need to take care? So the three aspects, the confidentiality, integrity, and availability, are the bedrock of security. When I say confidentiality, the data needs to be encrypted. Like when we send data, especially the personal data, see sometimes like we are not just talking about we think that okay, a patient's illness record, like it doesn't have much value. But then oftentimes like in biomedical systems, the illness record is also stored along with the patient's financial data and other information. And sometimes even illness record is confidential. It's not supposed to be made public. So what we need to have is like a strong encryption algorithm. Like a weaker encryption algorithm is again going to be compromised. Like we need to have a strong encryption algorithm. So here again, this is again a good topic of research, but it's slightly more far away from the biomedical applications, but it's a generic area of research. how to improve, like I mean, most of the encryption algorithms are like supposed to be NP hard, but with more advances in computing, some of the algorithms are already being compromised. So we are going to much more stringent algorithms, but they are coming up with power and area overheads. So how to come up with better encryption algorithms, symmetric keys, asymmetric keys, hashes. So how to come up with those algorithms is one area of research. The next aspect is very critical, the integrity. So how do I even, this is actually the word which, this actually goes with the word trust, like which Professor Patnaik mentioned. So first we need to have access control, like first of all, have proper access control to our systems, so that a person with not or a person or an entity which doesn't have the proper access controls is not even able to access the data present in our setup. The second one is authentication. So Dr. Patra briefly touched upon the subject called cloud. So in the cloud, what happens is, like, we have arrays of massive arrays of processors and accelerators and so on. So what if a person, like, who has a physical access to that cloud or the data center, embeds a device which can transmit all the data of a particular which can of a particular company or a particular hospital or so on. So we need to have authentication to make sure that a particular device has a good firmware. Like there is a lot of emphasis on what is called the secured boot. So this probably will fall into the domain of computer science today, but then, like, this needs to be worked with VLSI design. So the design has to ensure that, okay, only a secured boot happens in a device, and during an unsecured boot, like, the device just shuts off. And similarly, like, when somebody is like connecting a new device, that new device authenticates itself, like telling that, okay, this is the firmware and this is the company that signed the firmware, by using authentication keys. And second and lastly, the authorization. When authorization is like someone authorizing a person to access a particular, this is more in line with the access control. Like, authorization is a part where, like, we have embedded keys where only certain accesses are authorized and certain other accesses are not authorized. The third important critical aspect of security, I mean the collaterals of security, is the availability. So we have to make sure that all the equipments that we are designing, like they are available all the time. Like it cannot happen that, okay, there is a denial of service attack and certainly at certain times the equipment is not available. Or for example, we cannot say that, okay, if there is a hack, I'm going to shut down a certain heart-lung machine in a hospital, and that reboot is going to take 2-3 hours or 2-3 minutes also. Because, like, that availability should always be there, like shutting down and rebooting. So these are not some of the solutions that are possible there. So we need to make sure that this device is always available. And for that, like, we need to make sure that, okay, like, even the risk mitigation processes, some of the risk mitigation processes that we take. For example, we find that there is an attack. The risk mitigation doesn't mean that we shut down the system automatically. Like the system should, some parts of the system should still be available for the use of the consumer. So to handle all these things, there is a great bit of research which is going into what is called the root of trust and the chain of trust. So if you folks have a Windows laptop, and if you recently noticed that the Windows 11 update required what is called the TPM, like the Trusted Platform Module. So only those laptops which are having this TPM module were able to get the Windows 11 update. So this TPM is nothing but a chip. It's a microcontroller, like it's a real-time processor, and it's a real-time processor, and it stores all the critical cryptographic assets of the system. For example, all the keys that need to be exchanged, and all the signs, like for example, like different companies have different digital signatures. So all these digital signatures, they are all stored there, and and this TPM is a trusted module which is not hackable. Like and this is forming what is called the root of trust. And this TPM subsequently authenticates each of the device. And there are multiple, these days, like, device also come with some certain microcontrollers within the accelerators process all have a separate security microcontroller. And these microcontrollers are in turn authenticated by the root of trust. And then that builds the entire chain of trust. So this is another topic of interest, and where large amount of research is going on, how to build the chain of trust in different kind of applications. Like a cloud could be one where it's entirely a compute kind of application. Whereas like in a hospital scenario, like we add multiple different devices to our to a central controlling computer. But are all the devices like coming up with, are all the devices having a secure software? Like even if one of the devices not having a secure software, that is going to be the Trojan, and that's going to break the security of the entire organization. So this chain of trust is more critical, and how to build it for different setup is another area of interest. There are multiple standards and regulations. When I say standards, like standards are like prescribed way of doing certain things, but then the standard is not enforced. For example, I could have a standard for video coding, but I need not follow that, and I can have my own way of doing it. I can slightly deviate from the standard. But then there comes the regulation, where some body which is much higher up comes out and says that, okay, no, these regulations have to be followed, and the regulations also call out like what are the standards which are coming under that regulation. So what we see is like in the case of automotive, there has been a lead which is taken. Like we have a cybersecurity standard for automotive called 21434, and there is a regulation which is called the UN ECE, where UN stands for the United Nations, UN ECE R155 and R156. These mandate the participating countries to have cars which are adhering to this ISO 21434 standard. This kind of standard is not fully widely accepted in biomedical applications. This is another area of research that people can focus. So these are the things which I had for today. So let me see if there are any questions before I move on to the next few slides. Okay, used in where? Sorry.
Difference between stability and reliability.
Okay, stability is, we typically don't use the word stability in VLSI designs. It's more about the system design. Like reliability is like when we give a certain input, or when given an input, the transfer function of that device always produces the same output. So that is reliability. Like it should not happen that because of software error or any other errors or any fault which is happening in inside the chip, or it could be a physical fault or it could be a temporary fault. It should not happen that the device produces a different result any one of the time. So reliability is like producing the same result time after time. Stability is more of a stochastic term. Like, okay, like I have like 1,000 trials. By the way, that is not something that we work on in VLSI per se. Like, for example, stability, I would say that, okay, when we have, say, 1,000 trials, and then like out of that 1,000 trials, 990 trials, like it produces the correct result, 10 trials, like it's not producing the correct result. But then we say that the system is stable or quasi-stable. But that's more like a probabilistic domain, whereas reliability is like making sure that the answer is correct every time. Okay.
Sir, one more question, sir. Difference between FinFET and ferroelectric FET.
Okay, okay. I'm not this thing about ferroelectric FET, but the FinFET is like more of a okay. Well, the answer is like I don't know about the ferroelectric FET part. The FinFET is like more of I mean the next generation of a MOSFET, the planar MOSFET. Sorry, I don't know about the ferroelectric part, ferroelectric FET part.
Sir, working difference between MOSFET and quantum dot cellular automata, QCSL.
Okay, okay. Again, like fine. Quantum is a totally different paradigm altogether. Like in binary, we talk about like two states, like 0 and 1, and quantum is a totally different paradigm. And that is again something which I have not worked on. Like, so I will not be able to answer that question. Sorry.
So that's also in the.
Yeah, I just see one more this thing. Like, in your opinion, what is the best source to follow the recent developments in VLSI industry? Can you name a few sources we can get? Okay, I'll come to that. Like, there are certain conferences. Like, I've listed down certain resources here as well. Like, some of them are the articles which I referred for this, like this slides. NVIDIA has this conference called GTC. The GTC is a conference. Now we are going to have this GTC later this month, 19th to 22nd. And this is a very good source of information for generally about AI and NVIDIA products. So I'm sure if you can register for this conference, it will be very valuable, and probably you can ask the students also to register here. This should be a valuable source. Besides that, NVIDIA has the student program, university program, where NVIDIA takes part, can create the AI lab in universities, and the universities, the researchers, the academia and the company can collaborate. By the way, NVIDIA has investments in a lot of startups also, like AI and ML startups. Through a program called NVIDIA Inception Program, there is something called the NVIDIA Deep Learning Institute, where there are a lot of trainings about deep learning. So this is something that the faculty and students can get the benefit of. And if you're already using using AI and ML techniques, then there is something called the developer program, where it gives the entire software suite, and that can be downloaded, and even we can rent certain clouds. The GPU workloads can be rented on the Amazon or any other public cloud, and these programs can be implemented in the cloud itself. We don't have to purchase the hardware per se. So these programs enable students to implement their designs in a fraction of a cost actually. And the university program, actually it's a collaboration of the company with universities, the academia and the researchers. So I'm sure we can make use of this to the utmost extent. Okay, is any postdoc program in VLSI biomedical in NVIDIA? Sure, you can we can connect, and I can explore. NVIDIA has a group called NVIDIA Research. Some of the topics that Dr. Patra mentioned, we are also using that in our company, and that is a product of NVIDIA Research. So I can explore that, and I can help you connect to the right people there. How are we on the time? I think we are already short of time. Okay, that's all I had for today. Any more questions?
No, sir, that's all.
Thank you all. Thank you for the patience. I hope it was useful, and thanks for the opportunity once again.
Thank you, sir. Respected sir, on behalf of Bangalore Institute of Technology and ECE Research Center, I extend vote of thanks to our esteemed speaker, Satnarayan Balaji, who spared time from his busiest schedule to grace the occasion. Today, we had an opportunity to hear your thoughts, and this will surely be going to encourage us in our future events. Thank you, sir.
Thank you.
So, dear participants, afternoon session is hands-on session using Python. So please, all of you, be ready with your laptops. So afternoon session will start at 2 o'clock.
Thank you very much, sir.
Thank you, madam. Yeah, thank you.